Hello all, my name is Krish Naik and welcome to my YouTube channel. So guys, here is a one-shot, complete, in-depth mathematical intuition about transformers. I know many of you were specifically waiting for this particular video. This is a 5 hours tutorial. Along with this, I'll be providing you the complete materials that I've actually written. The in-depth mathematical intuition along with examples, along with diagrams, everything will be included over here. So yes, go ahead and enjoy this particular session. Make sure that you also go ahead and write your notes and make sure to share in the LinkedIn and definitely do tag me and I will just try to come and see that how your learning process is going on. So yes, this was it. Let's go ahead and enjoy this particular session. Hello guys, so we are going to continue the discussion with respect to NLP with deep learning. In this video and in the upcoming series of video, we are going to discuss about transformers. Now, transformers is a very important topic. Please keep a note of that. If you really want to excel in deep learning, specifically with respect to NLP task, then transformers is the thing. In this video, I'll just show you a plan of action, like what all things and how we are going to cover this entire topic. Till now, we have already discussed about RNN, LSTM, GRU, RNN. We understood what were the problems over here, right? Then we went to encoder decoder architecture, which was in sequence to sequence learning. Then over here also we faced some kind of problems, and then we tried to solve that particular problem through this attention mechanism, right? Again, on all this architecture, there was some or the other differences, right? And now finally, we will first of all understand what is the problem in attention mechanism and what kind of problem we are solving it with the help of transformers. The plan of action will be that first of all, we will go ahead and understand why transformers. Then we will see the architecture of the transformer. So this is the detailed architecture, which is basically shown on the right hand side. And this architecture looks really cumbersome, right? Probably if you're seeing it for the first time, there's so many things over here. And it does not even match from the architectures which we have learned in encoder, decoder, or attention mechanism. Don't worry, we will break this down, the entire architecture. So in this architecture also, you have this encoder, you have this decoder. But inside the encoder and decoder, there are many more things that is actually included, which we will be discussing about it, right? So the plan of action will be that first of all, we'll try to understand why transformers. Then we will go with the architecture of transformers, wherein the first module that we are going to cover is something called as self-attention. In this self-attention, you will be seeing this key QKV parameters. So we will also be understanding what exactly this is. Okay, we basically say this as query key value pairs. Okay, what exactly it is, we'll discuss about it. Then we will be talking about positional encoding, right? This is also a very important topic in this architecture. Then we will be covering about multi-head attention. And finally, we will be combining all these topics to understand the working of the transformers. So this is the plan of action, how we are going to cover this particular topic. But just to give you an idea why transformers is really important, because right now, if you have heard about generative AI, right? And the kind of LLM models or multi-models that are available in generative AI, right? Most of the models, these are basically trained on by using this transformer architecture, right? Specifically, if I talk about some of the models like BERT, or if I talk about GPT, right? And if you know about GPT, right now, OpenAI has come up with this amazing models, right? OpenAI, specifically your ChatGPT applications. And right now, the model that it is using is nothing but GPT 4.0. Right, 4.0. So this specific model, it is based on the transformer architecture, but it is trained with huge amount of data. And obviously, if I talk about this GPT, it is like GPT-4 is using this GPT architecture along with the transfer learning with respect to this particular architecture, which is trained with huge amount of data. So we will be covering all these topics, but in this video, I just wanted to give you about the plan of action, how we are going to cover each and every specific topics. So yeah, this was it. In my next video, I will be talking about why transformers. And again, before that, we really need to again revise this encoder decoder architecture and attention mechanism. And what is the problem that we are facing over here? We will be talking about it. Hello guys, so we are going to continue a discussion with respect to the transformers. So this is the first topic that we are going to pick up and we are going to understand. So here I've also given the definition. So that is the reason I've written what and why in transformers. So if you really just want to understand a simple definition about this particular architecture, it is nothing but in transformers in natural language processing are a type of deep learning model that uses self-attention mechanism. Please keep a note of this because this is really important. To analyze and process natural language data, they are encoder-decoder model that can be used for many applications, including machine learning translation. Now, if I talk about machine learning translation, this is specifically something called as sequence to sequence task, right? Now, when we say sequence to sequence tasks, let's say I want to solve a problem statement. One of the example that we can probably take is like language translation, right? Language translation. And if you probably go ahead and see an example of Google Translate, right? This is a task of sequence to sequence task. It is a sequence to sequence task because if I really want to convert from English to French, right? English to French. So in this scenario, you'll be able to see that my input with respect to English will be many words. I will be having many inputs over here. It will be many, and my output will also be consisting of many words. So this basically becomes like a many to many sequence to sequence task, right? Now, when we have the sequence to sequence task, and obviously length of the sentences is also a meaningful thing over here, right? Length of the sentence. Now, as the length of the sentences increases, we should be able to solve this particular problem again with a very good accuracy. So in this kind of task, usually transformers is used, okay? But you may be thinking, Krish, fine, you have also told that in the previous architecture of encoder-decoder, you told that this is also used for sequence to sequence task. And if I talk about encoder and decoder, like they were, if I just probably go ahead with this particular diagram. So I had an encoder over here, right? And I had a decoder over here, right? So in encoder and decoder, what we used to do, we had our LSTM, right, over here. And based on this LSTM, when we used to go ahead and pass this entire sentences, okay, please remember, we do not take the output in this, right? So if I just go ahead with a basic architecture of encoder decoder, you'll be able to see that if I used to give my words over here, let's say x1, x2, x3, and this words we used to give based on timestamps. T is equal to 1, T is equal to 2, T is equal to 3. So let's say if this is my sentence 1, which is having this particular words. And again, we used to convert this entire words by using some embedding layer. Okay. Convert this into vectors. Okay. And then pass it to the entire LSTM. So this was my LSTM over here, right? And this is my encoder and this is my decoder, right? So after doing this, finally, you should see that we were able to generate one C vector, that is context vector, right? So here I will just go ahead and generate this context vector. And based on this context vector, we used to provide it to our next decoder layer, right? Next decoder layer, which used to have this LSTM, okay? So here is my decoder completely. I will pass it over here. And then with respect to this particular decoder, I used to also get my output. And here we used to use some kind of Softmax, right? Now, this was the basic architecture of the encoder decoder, right? And this is what we used to do. This context usually used to define when we are passing every words based on the timestamp, the final context that we used to get at the end of this particular sentence used to represent this entire sentence itself, right? Which is consisting of this entire words. And this context was further sent to our decoder model. And this decoder model would use to do the prediction based on this context that we have. And along with that, we used to also calculate the loss. Everything was discussed, right? Based on the encoder architecture. But one problem we understood from the encoder decoder was that this context was not sufficient to represent this entire sentence if the sentence length increases. If this increases, the C context was not at all sufficient, right? And this was the problem with respect to the encoder decoder architecture. And that is the reason you could see that our blue score was decreasing as the length of the sentences was increasing. So this I've covered in my previous video. I would suggest if you want to quickly revise it, you can go ahead and do the revision. Okay. Now, for this, we also had seen an architecture. So here was my sequence to sequence learning. This was the entire research paper of this, how the entire working actually happens. Each and everything was explained clearly over here, right? So after this, what we did is that in order to solve this problem of the context that we had, like our main idea was that, okay, we should not create the entire context at once and probably send it to the decoder model. Instead, what we can actually do is that we can use something called as attention mechanism. And that is where this research paper came, right? So based on this research paper, what we exactly did was that the plan was very simple. Instead of just giving a single context, we had to actually provide an additional context to our decoder. And this was the architecture we specifically discussed about. And if you remember, in our previous videos, we have discussed the entire mechanism, now how this attention mechanism actually works, right? And we discussed about this entire research paper over here. So here was the entire working, wherein along with a single context, we also have to provide additional context, create our alignment scores, create our attention weights, and then pass it to the decoder. Okay. And that is what we specifically solved it with the help of attention mechanism. So let me do one thing. Let me just take this screenshot. Okay. So that you will be able to see this reference over here. So here I will just put this reference, and here also I have added this additional reference. So this was all possible because of your, the attention mechanism, right? So this is the entire working, right? And with the help of this, what we were able to do is that we are able to provide additional context to the decoders. And then this decoders, what they were able to do is that they were able to do the prediction, and the problem with respect to the long sentences, right? The problem of accuracy that we were facing, it started increasing, right? Because of this research paper. But still, let's understand with this attention mechanism. Okay. So here we are using bidirectional LSTM RNN. Here also we are using LSTM itself. One problem that we see with this attention mechanism or encoder decoder, okay, attention mechanism or encoder decoder, is that we pass every words based on timestamp, right? So here parallelly we cannot send all the words in a sentence, right? And again, because of this, see, over here you'll be able to see even in encoder decoder, we used to send the words based on timestamp, right? Now, when we are sending the based on timestamp, at t is equal to 1, I'm sending one word, t is equal to 2, I'm sending another word, right? Similarly, over here in this bidirectional LSTM also, I'm sending one word at a various timestamp. We won't be able to do the entire execution or this entire training parallelly, right? And because of this, yet your attention model is not scalable. When I say scalable, that basically means if my data set is huge, right? Still, the encoder decoder attention mechanism will not be scalable with respect to training. And this is really important to understand, because the new models that we'll be seeing with respect to transformers uses something called as, they never use this LSTM RNN in encoders or decoder, right? What they use is that they use this something called as self-attention module. And because of this self-attention module, you'll be able to see that all the words will be parallelly sent to the encoder for further processing, right? And that is what this architecture comes into existence. See over here in the input embeddings, right? You're sending all the input all at once. So it is supporting this entire parallel execution. And that is where, because of this, we'll also be learning about one more topic, which is called as positional encoding. positional encoding. We'll discuss about this as we go ahead, right? And this will also play a very important role for this when we are sending all these words parallelly, and how each and every word vectors is going to get computed. We'll discuss about this. What exactly this self-attention module will be doing, we'll be discussing about it, right? Now, you should definitely understand over here is that in attention mechanism in encoder decoder, we are not able to do this. Hence the word scalable. Now, when we say scalable, that basically means why these transformers are really performing well is that as we keep on increasing the data set, you'll be able to see that we are able to get some amazing models, amazing state of the art models. I'll say SOTA models, right? So state of art models we will be able to get specifically with respect to NLP task. Now, this is not just restricted to NLP task. With the help of transfer learning, right? With the help of transfer learning. Now, transformers are even used in multimodal. Okay, they are used in multimodal tasks. Multimodal task basically means task that has both NLP plus image. So here also they are able to perform really, really well. Okay, how it is able to perform and all, we will understand once we understand the entire architecture. But this is the major important thing that you really need to understand. Why transformers? What was the problem that we had in our previous models like encoder, decoder and all? And this is one of the very important problems that we have, right? So just defining all these things, since it solves all these problems, you'll be able to see now everywhere this entire transformers have really changed the AI space. Now you'll be able to see a lot of SOTA models, right? And this SOTA models is nothing like, let's say, some of the transform models that we have, which is already trained in huge data set, is like BERT, GPT, right? Now, what companies are doing, if they really want to create their own model, they don't have to train it from scratch. And these models are trained with huge data, right? They can directly just use transfer learning. And with the help of this transfer learning, they are creating this amazing sort of models, right? State of art models, right? And the architecture, this is completely based on transformers itself. And as I said, multimodal task, the same architecture is also used with respect to images. So if you see in OpenAI, some of the application like DALI, right? They actually just based on a text, they are able to generate the images, right? Entirely, it is completely based on transformers. So just to give you an idea, this will also be very much important because based on this architectures, various LLM models are also used in generative AI. Okay, generative AI. LLM basically means large language models. So I hope you got an idea. Just take this into consideration. This is a very important thing that we have discussed. Parallelly, we cannot send all the words in a sentence in attention mechanism or encoder decoder. But with the help of transformers, we are not at all using LSTM RNA. Instead, we are using self-attention module. And this self-attention module functionality will be that we will be able to send all the words, right, parallelly for the further processing. What exactly happens in the self-attention module, we'll discuss more about it. Okay. So I hope you got an idea about this. One more very important problem that we see in transformers, that is with respect to contextual embedding. Contextual embeddings, right? Now, what exactly happens in contextual embedding? We will discuss about this. Okay. Now, with respect to the contextual embedding, let me just give you an example in order to make you understand this. Okay. Let's say I have a sentence. My name is Krish and I play cricket. Okay. Now, let's say over here, when I pass this entire information, right, in my embedding layer, let's say this is my embedding layer. Now, in embedding layer, when we pass it, our main task will be that from this embedding layer, for every word, we should be able to get vectors, right? Some vectors. So If I pass my, then name, I should be getting another vector. Is, I should be getting another vector. Krish, I should be getting another vector, and I should be getting another vector. Based on timestamps, I will be getting this kind of vectors. And understand, if you are specifically using embedding layer, and let's say if this embedding layer is using some word embedding techniques like word to vec, for every word we are going to get a fixed vector. Okay, so this, if my is there, then I will be getting a fixed vector of some dimensions. Similarly, name is there, I will be getting a fixed vector. Okay, is there, I will be getting a fixed vector. Krish is there, I'll be getting a fixed vector. And is there, I'll be getting a fixed vector. I will is there, I'll be getting a fixed vector, right? And similarly, play is there, I'll be getting a kind of vectors itself, right? All these words will be represented in some kind of vectors. Now, I need to make you understand about contextual vectors. What exactly is this contextual vectors? See, it is always a good idea that if you are able to get a vector, it is fine, right, for every word. But we should always try to get a vector whenever we have a longer sentences based on the relationship with other words. Now here you can see my name is Krish and I play cricket. Okay, I is obviously related to Krish. There are some kind of relationship, right? So if I probably give this same word on my contextual vector embedding, vector embedding, then all the vectors that I will be getting, this vector should be having some kind of relationship with respect to the other words. Like Krish and I, here there is a very strong correlation, right? So some context will be there. I play cricket, so cricket is also there. So this cricket vector, I should not be getting a fixed vector itself. I should be getting a vector which should be related to Krish. Based on this particular relation, there should be some changes in this particular vector which suggest that, hey, there is some contextual dependency in this particular word, right? And this entire problem is solved by our self-attention. And because of this, you'll be able to see that our transformers will be damn more accurate, right? And we'll be talking more about this self-attention model in the upcoming video. But if I talk with respect to the most two overall problems, why transformers are specifically used. One is, here in transformers, parallelly we can send all the words for processing, because of which it makes the entire model scalable with respect to training with huge data sets. Okay. The second thing is that it has this contextual embedding thing, right? Which was basically missing in encoder and decoder. Because in encoder and decoder, we just used to use an embedding layer. We used to pass each and every word, get a vector, and further do the processing with respect to this. But now with the help of this self-attention, you'll be seeing that we'll be able to even create contextual vector embedding. Hello guys, so we are going to continue a discussion with respect to transformers, and in this video, we are going to discuss about the architecture. Over here on the right hand side, you can see this complex architecture over here, okay? And obviously, you may be thinking this is very, very difficult, but what I will do is that just directly going and seeing this architecture, instead of this, I will try to break down the entire architecture step by step. And as I said, what all things we are going to learn, right? That entire plan of action that I've actually created to understand the architecture of transformers, then we'll be understanding self-attention, positional encoding. We'll go step by step with respect to this. To start with a basic transformer architecture, let's consider this particular block diagram. So this is my transformer. This transformer will be used to solve our sequence to sequence task. Okay. And in this case, the task that I am probably considering will be language translation. And I will be translating, let's say, from my English sentence to my French sentence. Okay. So I am planning to do this particular task. Okay. So here, when I say input, that basically means I'm going to give my English sentence, and this is probably going to convert into a French sentence. Okay. So this is what a transformer does just by seeing this block diagram. But the main thing will be that what is inside this particular block diagram. So let's go ahead and first of all see this, what is inside this particular block diagram. So if you go down here inside this block diagram, that is the transformer, you have something called as encoders and decoder. So this also follows a encoder and decoder architecture. Decoder architecture. Okay. It follows this specific architecture. Now, what is inside this encoder? When we say encoder, is there only one encoder? Or when we say decoder, is there only one decoder? Nothing as such. Inside this encoder, you may have multiple encoders like this. Okay, like this, you may have multiple encoders. And your text input that you're specifically giving over here in this encoder will be going from one encoder to the other encoders. Okay, something like this. So this is my entire encoder over here. So this entire encoder I have actually drawn in this particular way so that you'll be able to understand. Okay. So here I will be having multiple encoders step by step. Like in the research paper, that is attention is all you need. Let me just show you the research paper. So this is the research paper that we will be looking at, attention is all you need. And this particular research paper, if you probably go ahead and explore it, right? Here, specifically, we are going to talk about this particular transformer, where we'll be learning about positional encoding, self-attention, multi-head attention, feed forward, all these things, right? So this what is scaled dot product attention, multi-head attention. So based on this particular research paper, I will be probably explaining each and everything. So as I said, when we talk about an encoder, so here I will be having multiple encoders where my information will be passed from bottom to top completely. And then from this entire encoder, I will be passing all the information to the decoder. Similarly, decoder will also have, it's just not like one block. It may have multiple decoders. Okay, like this, it may have multiple decoders one by one. Okay, what is inside this decoder, we will get to know in some time. Okay, and one by one, we'll be passing this particular decoder information on the top, and finally, we should be able to get our output. Okay, so this is what exactly it is. Okay, and you'll be able to see that from encoder, we'll be passing the information to the decoder also. Okay, and this entire architecture, when I say, right, in the research paper, it is shown that we are going to use 6 encoders. Okay, 6 encoders, and parallelly there will be 6 decoders. Okay, so what is there in the research paper also, it's not like it needs to be 6, but in the research paper, when they created the research, they have used 6 encoders and 6 decoders to do this entire task. Okay, now here in the encoder, I will be giving how are you, and then in the decoder, it should be able to give me the French translation of this English sentence. Okay, now the question rises, what is inside this encoder? We should definitely understand. So inside this encoder, if I go to my next block diagram, here you will be able to see in a single one encoder, in a single encoder. So inside this particular encoder, you'll be seeing that there will be one self-attention layer and there will be one feed forward neural network layer. Okay. Again, try to understand this basic level of understanding. I've drawn this particular diagram in a very simpler way. So there will be one self-attention. We'll be understanding what exactly is the self-attention. We'll try to see like what is the exact working of this as we go ahead. Then from this self-attention, it is connected to the feed forward neural network. And if I consider just a single decoder, right? So inside a single decoder here, you'll be able to see that I will be having a self-attention. Also, I'll be having a feed forward neural network. But along with this, I also have an additional layer, which is called as encoder decoder attention. Okay. So we will be understanding this entirely. Don't worry, but we just need to understand this basic architecture, what exactly it is. Now let's go ahead and let's try to see what this self-attention actually does. And that is what we are going to discuss in this particular video. Okay. Why this self-attention is basically used. Okay. Now with respect to this self-attention, you'll be able to see that if I go down and if I still explore more about the encoder. So here, this is my encoder. Okay. This is my entire encoder. So as I said, in my encoder, I have a self-attention and then I have a feed forward neural network. Now let's say that I have a sentence over here. How are you? Okay. So this is my sentence that I'm actually giving it over here. How are you? Then this self-attention, first of all, we need to convert all the words into vectors, right? So this is my vectors. This is basically getting converted. And here we can use vector embeddings, or we can use an embedding layer, whatever layer we specifically want, right? Let's say here we have like embedding layer. We have an embedding layer, and this embedding layer is responsible in converting a word into vectors. So each and every word is basically converted into a vector over here. Now, as I pass these words to this self-attention layer, this will convert this particular vector into a different vector. And this vector is basically called as contextual vectors. Okay. So let's understand the differences between this vector versus the contextual vector. This is really important to understand. Okay, we'll try to understand this in this coming section itself, right? So here the self-attention is doing a very simple task. It is taking the vector of a words and it is converting this entire vector into another vector like z1, z2, z3, and this vector is nothing but it is called as contextual vector. Why do we say this as contextual vector? Because these vectors are not similar to this particular vector, but these vectors, you'll be seeing that it will be with respect to context of different words also. It will consider the context of different words also. Okay. And that is the reason we will probably be getting a different vectors over here, which we specifically call it as contextual vectors. Okay. So I hope you got an idea about this. Okay. And once we get this contextual vector, we send it to the feed forward neural network. So this feed forward neural network here, you can see over here, I will be passing this particular vectors over here. Here, okay, and each and every vector will be passed to this particular feed forward neural network, and I should be able to get my output. Let's say this specific output that I am getting, right, I will be considering it as my another vectors. We will discuss about it, why exactly this is required, and then this will be sent to my next encoder. So I will just try to draw this, or I will just try to draw in this way. So this will be sent to my encoder 2. So this is my encoder 2. This is my encoder 1. Okay. And here it is be sent to my encoder 2. Then again, the encoder 2 will be having a self-attention. Okay. So here it will specifically have this self-attention again, and along with this self-attention, it may also have a feed forward neural network. So it will still keep on continuing. So I will not draw this diagram because you know that what it will be available in my encoder 2. Okay, perfect. So this will be passed over here. So here you can see that I will rub this, and this information is going to pass over here. Okay. And this is my neural network. This is my feed forward neural network. Neural network. Okay. And here you can see all this information is basically passed through this. This passed through this. Okay. So this is the entire basic architecture about the encoder itself. So let me just go ahead and repeat it. So initially I had a transformer. The transformer is nothing but it is a combination. It is having this encoder and decoder architecture. So here I will be having my encoder. Here I'll be having my decoder. Now inside my encoder, like this encoder, it can have multiple encoders like this, 1, 2, 3, 4, 5. And even in the research paper, they have used 6 encoders. And similarly in the decoder, you'll be seeing that I'll be having 6 decoders over here, which are stacked one by one. Okay. Then what happens inside this encoder that we have? It has 2 important layers. One is the self-attention layer, and then you have the feed forward neural network layer. The self-attention layer, you know, we don't use LSTM or RNN like how we used to use in the encoder decoder architecture. Instead, we have this self-attention layer. In the decoder also, you'll be able to see that I will be having a self-attention feed forward, but between that, there'll be something called as encoder decoder attention. Okay. Then if I go forward and try to understand what exactly this self-attention does, it takes a fixed vectors, right, of a word, and then it converts this entire word into contextual vector. The contextual vector is very simple. Why we are actually changing? It is just giving an idea that contextual vector means what? all these vectors that is basically getting converted over here, or whatever vectors you are getting, this will also have, these vectors will be defined in such a way that it will be based on the context of other words. Okay. Here, what is the difference between this vectors and this vector is that here we don't have any context, right? Here they are fixed vectors. If you are using some embedding layer, how word is basically determined by a vector, that will get converted, right? How R is defined, that will get converted. How U is defined, that will get converted. But by using this self-attention, the vectors that I'm able to get is that how we'll be having a vector considering the context of the other two words. Okay. Similarly, this particular vector that I'm actually getting, it will be based on the context of other words, how and you. Similarly, the third word, right? And that is nothing but my contextual vector. Now, why do we require contextual vector? As I said that whenever you have a longer sentence, it definitely helps you to work, it helps you to get a model that will provide you an amazing accuracy. Okay. And that is the reason we are using this, right? And the next important thing, as I said, when we were discussing in encoder decoder, we cannot pass the words parallelly, right? One by one we pass it, then we generate the context. But in this case, since we are using this self-attention layer, here all the words will be passed parallelly. Okay, all the words. So at a time we are passing it, and this makes this entire architecture scalable. Now, my next important discussion in this particular video will be that let's discuss more about self-attention. Okay. Now, what exactly self-attention does, we will try to discuss this at a higher level. Self-attention at a higher level. And that is what we are going to discuss in our next video. But I hope you got an idea with respect to the architecture, what exactly it is. The first thing that we will be discussing, that how this entire vector is basically getting converted into a contextual vector. And why contextual vector is required? Because it gives a proper context of the words that I'm actually passing. And all the words are basically passed in a parallel mode, right? Hello guys. So we are going to continue the discussion with respect to self-attention. And already we have seen the basic architecture of transformer. Now we are going to deep dive into the self-attention layer, and we'll try to understand how exactly this works. Now, this session and the upcoming session, we are going to probably discuss a lot about self-attention, where we'll also be solving like how this entire self-attention layer actually works, all the mathematical intuition behind it. And through this, I am definitely sure that you'll try to understand, or you'll get to understand how the contextual embedding is specifically created. Okay. So again, the idea behind self-attention, what exactly it is. So first of all, here you'll be able to see that, let's say I have the self-attention layer. Okay. Now with respect to this self-attention layer, whenever we give any vectors, right? Let's say the word is like the, cat, sat, right? Let's say if this is my sentence that I'm actually giving. Okay. Now with respect to this particular sentence, you'll be able to see that when I am giving this specific sentence, this words that you'll be seeing one by one, which I'm actually giving, this will first of all get converted into vectors. So let's say I'm converting this into vectors, and here also we will convert this into vectors. Let's say that right now the default vectors for the is like 1 0 0, for cat is 0 1 0, and for sat is 0 0 1. Okay. Now as soon as we pass through this embedding layer, not embedding layer, it's the self-attention layer. Okay. As soon as we pass through this self-attention layer, then from here we should be getting the output. Now the output that we should definitely be getting over here will be another vector, and this vector that we specifically get, this is our contextual embedding. And why do we say this as contextual embedding? Because see, here we are going to take the importance of different tokens, right, in the input sequence, and we are going to create this particular vector. So right now, if I just consider this as an example, let's say this vectors gets converted as 0.8, 0.3, 0.4. Then this particular vectors gets converted to, you can just say that as 0.4, 0.6, 0.2. Okay, I'm just saying as an example. And this particular vector gets converted as 0.3, 0.4, 0.8. Now, what is the importance of getting this specific vector? It is very much, it is just simply, you can consider that here the entire, here the self-attention, what it is basically doing is that it is also specifying some importance of the other tokens or other words, and it is displaying or it is creating this particular vectors. Okay. So first of all, let's see this entire definition. So here it shows self-attention is also known as scaled dot product attention, is a crucial mechanism in the transformer architecture that allows model to weigh the importance of different token in the input sequence related to each other. So here we are just not going to keep our embedding vectors fixed. Instead, we are going to change all these embedding vectors into contextual embedding vectors based on the importance of all the other words, right? And this is what we are doing. And why do we do this? Because see, with respect to different sentences, different paragraphs, right? All the paragraphs, all the sentences will have different context. There may be importance of some other word. One word will be dependent on the other word itself, right? And because of this, right, you will be able to see that we'll be able to efficiently create applications like language translation, right? Language translation and all, right? Language translation or text summarization. This kind of use cases we will be specifically be able to create. Now, how to convert this to this, right? And the entire self-attention works on the concept of scaled dot product attention, right? So this is the entire operation that it specifically takes. Here, one by one, we will be discussing what is this Q, K, V, right? These are some vectors. Why do we use this specific vectors? But at the end of the day, this is the entire operation that we are doing. Now, what we are going to do is that we are going to see that how the self-attention layer is going to convert this vectors to this vectors, right? Which is a contextual embedding. But here, just to give an idea, this vectors has basically been changed because considering the importance of different tokens. Okay. Now let's go ahead and let's talk about self-attention in detail. So let's go ahead and discuss about self-attention in much more detail, right? And over here, our main aim is to convert this particular vectors into contextual embedding vectors, right? Now see one thing. Converting this particular word into a vector, right, into a dense vector like this. Here for this particular scenario, we can use embedding layers, right? So in embedding layers, what happens based on the dimensions, right? We will be able to get a fixed vector for each and every word, right? Like for the cat, sat, right? We can actually get the fixed vector. But getting this contextual embedding vector based on the context of other words, it depends on the entire sentence or it depends on the data set that we have, right? So how, with the help of this sentence or data set, we will be able to convert from this vector to this vector, right? So for this, there are multiple steps that we really need to follow, okay? So let's talk about this specific step, and that is where this entire scaled dot product attention will come into existence. So the first important thing that we really need to do is that we need to create or we need to derive three important vectors. So I will first of all talk about this inputs. So in the first step, we need to derive our three important vectors. One is queries, then I have keys, and then we have something called as values. Okay. So queries, keys, and values, right? Now, what is the importance of this query, keys, and values? That we will try to understand. Okay. For every word, if we are trying to convert that into a contextual vector, for every token, we specifically create a model, right? And this model will be computing these three important vectors. One is queries, one is keys, and one is values, vectors. Okay. So guys, now before we go ahead, let's go ahead and understand or see the basic definition of this queries, keys, and values vector and what is the importance of this. Okay. So here you'll be able to see, first we will understand about query vector. Now what exactly is a query vector? A query vector represents the token for which we are calculating the attention. Let's say for the first word that I'm actually passing if I really want to probably calculate the attention for this, which is the output vectors, right? Which we say it as contextual embedding vectors also, right? So in order to calculate this, we will specifically specify this vector as our query vector. Okay. Then they help to determine the importance of other token in the context of the current token, right? So in this particular token, the importance of the other token will be also specified, the final vector that we'll be able to get. Now, what is the importance over here? Focus determination. This is the first importance. Queries help the model decide which part of the sequence to focus on for each specific token, because there will be multiple tokens in a sentence. By calculating the dot product between a query vector and all key vectors, the model assesses how much attention to give to each token relative to the current token, right? So what we do is that we multiply this query vectors, or we do a dot product. I'll not say multiply. We do a dot product of query vectors to key vectors. And this helps us to determine how much attention to give to each token related to the current token, right? So if I have if I have cat, right? If I have sat, let's say this is my three words. So this initially becomes my query vector for this particular, if I'm calculating the attention for this. And the final vector that I'm actually going to get is that when I multiply this query vector with the key vector, right? The model will be able to assess how much attention to give with respect to all the other tokens that are there relative to this particular token, right? So that is what query vectors will talk about, right? And as we see more examples, you will be seeing that I will be solving a step by step, like how this entire query vector will be calculated, key vectors will be calculated and all. So second important thing is that with respect to contextual understanding, queries contribute to understanding the relationship. This is very important. Relationship between the current token and the rest of the sequence. This is the most important thing. Query vectors actually contribute to understanding the relationship between the current token and the rest of the token, which is essential for capturing dependencies and context. Okay. Then coming to the key vectors. What exactly is key vectors? Key vectors represent all the token in the sequence and are used to compare with the query vector to calculate the attention scores. Now, what exactly key vector is? It will have all the tokens that is probably there in the sentence, right? And it is basically a query will be compared to this key vectors to calculate the attention score. What exactly attention score is, we will discuss about it, and how to calculate it also we'll discuss about it. So let's talk about the importance of key vectors. Keys are compared with queries to measure the relevance or compatibility of each token with the current token. This comparison helps in determining how much attention each token should receive. Okay. Information retrieval. It also plays a critical role in retrieving the most relevant information from sequence by providing a basis for attention mechanism to compute similarity score. So what we do is that we take a query vector, we can directly query from this key vector itself, and based on similarity scores, we get the most relevant information based on the dependency of all the other words also. Okay. And finally, the value vectors. Value vectors holds the actual information that will be aggregated to form the output of the attention mechanism. Okay. So value contains the data that will be weighted by the attention scores, the weight sum of the values from the output of the self-attention mechanism. So we will discuss about all these things as we go ahead, but I really wanted to put a basic definition of key query, key, and value vectors. Okay. Now let's take one specific example, and by that you will be able to understand how we are going to create this query, key, and value vector. Okay. So let's say I have an input sequence. So let's consider this is my input sequence, and the input sequence is nothing but it is having this word, the cat sat. Okay. So this is my input sequence. Right now, let's say we are just going to take the embedding dimension by the embedding layer. So the embedding size, I'm going to probably take it as 4. That basically means for every word, we will convert this into 4 vectors. Okay. And even for the Q, K, V vectors that we are also going to compute, let's consider this also as 4 dimension. Okay. So I'm just going to consider all this as 4 dimension. So here you will be able to see that how we will be able to generate this KQV. We will try to see. Okay. So first of all, the first step over here is something called as token embeddings. Okay. Token embeddings basically means whatever sentence we have, we will try to convert that into some kind of vectors. So let's say I will be writing E of the embedding of the. Okay. Let's say that here there are 3 words, but I am considering there may be 4 dimensions. So I will just go ahead and mention, hey, the is represented like this. Okay. Then I will be having E of cat. Let's say cat is represented something like this. And then I have E of sat. 1, 1, 1. Okay. So this is how the entire tokens is basically represented for this particular words, and these are my fixed vectors. Okay. Now the second important step is that see guys, one very simple thing that you really need to understand. If I want to convert one vector into a context vector, okay, by using this self attention. See, this is my one vector, right? Let's say if this is 1, 0, 0, I need to convert this into 0.8, 0.2, 0.3, right? This vector is basically getting created based on the context of all the other words also, right? So there is a huge dependency on the entire sentence, right? Because with respect to different data set, there will be different sentence. And based on different context, different dependencies, this vector will keep on changing, right? So we should definitely come up with a model wherein I will say this model as self-attention, where I give one kind of input and I should be able to get my contextual embedding based on the sentence. This will have all the information about all the other words also. And that is why the reason we are using this query, key, vectors, value vectors. That is the reason for that. So that it has some information about the other words and sentences also. Okay. So now once we have done the token embedding, so that is what we are doing. Now we will try to create this entire model, and I will also show you how this model will be trained. The second step is something called as linear transformation. Now what this linear transformation basically does. Okay. So here you will be able to see, we will create query, key, value vectors by multiplying. See, I am telling you, we have to create a model. When we create a model, right, definitely a model needs to have some kind of weights. Because if I just want to convert a word into a fixed vector, we can directly use word to vec or some kind of embedding layer, right? And but here our scenario is something different. We need to create a contextual embedding based on the other words, and we need to do it in a runtime, right? So we have to probably train a model which will be able to take this particular fixed vector and convert that into a contextual embedded vector. Okay. So for that, we perform in the second step that is called as linear transformation. Here we create query, key, and values by multiplying the embeddings, by learned weights matrices. I will try to denote this matrices as W of Q, W of K, and W of V. Okay. weights of queries, weights of keys, and weights of values. Okay. Now, what does this basically mean? So this is very simple. Let's say if I have a vector, let's say this is my word of cat. Okay. I will take this cat vectors. Let's say it is 1, 0, 0. I will probably take a weight. Let's say this is my weight W of Q, right? If I take this vector and do a dot operation with this, I should be able to get my key vector, query vectors. Okay. I should be able to get my query vectors. So this will basically be my query vectors. Okay. So this is 1 cross 3. This is 3 cross 3. If I do a dot product, it will be nothing but 1 cross 3. Okay. Similarly, if I consider about my another weights, in order to compute the key value, the key vectors, I will multiply with a weight matrix or do a dot operation with respect to weight matrix for this particular vector, and I should be able to get my key vectors. Okay, so this basically becomes my key vector. And similarly, if I go ahead and consider my another weights, that is nothing but values, W of V, I should be able to get my V vectors. Okay, so this is what we are doing. So we create a Q, K, and V by multiplying the embeddings. This embeddings will be done as a dot product with respect to this particular vector, then this vector, and this vector. Okay, and then we'll be able to get this K, Q, V. But understand, here we have written learned weights. That basically means initially we'll go ahead and initialize the weights, and later on with the help of back propagation, this needs to be learned to get the exact right kind of key queries, key, and value vectors. Okay, and that is what we are specifically doing. Now if I really want to show you one practical application or example, let's go ahead and do one thing. Okay, so here is my token embedding, which I have actually considered. Now let's consider I've initialized W of Q, I've initialized W of Q, W of K, and W of V is equal to identity matrix. So identity matrix in this particular case, if I'm taking 3 cross 3, this will have all the diagonal elements as 1 and remaining all as zeros. Okay, so this can definitely be an identity matrix. So let's take this identity matrix, let's probably initialize it. Now you'll be able to see that if I really want to compute the query of the, right? So the is nothing but you'll be able to see that right? So in this particular scenario, if I just take this the is nothing but this 1 0 1 0. Okay, so here I'm going to basically write 1 0 1 0. If I do a dot operation with 1 0 0 0 1 0 0 0 1, right? So in this scenario, if I do a dot operation with this entire operation, then I know with respect to the identity matrix, I'm going to get the same value. Similarly, key of the, right? If I really want to find out the vectors, again, I will be able to get the same thing. Then value of the, again, I'm going to get the same thing, right? So in this scenario, you'll be able to see that with respect to the key, query, and value, if I'm multiplying this with my, or if I'm initializing and identity matrix, I'm actually going to get the same value. Okay, so this is the first step, right? Similarly, if I go ahead and compute, so this is my first thing where I have actually computed the key of the, queries of the, key of the, and V of the, right? It will be nothing but it will be 1 0 1 0. And this, how we have actually computed, very simple. We have taken our vectors, the embedding vectors, and we have multiplied with the identity matrix. Okay, or we have done the dot operation. Now, similarly for the other word, let's say the other word is nothing but Q of cat and K of cat and V of cat. It is not compulsory that you need to initialize it as an identity matrix. You can initialize anything, but just for my computation, I've made it like this, right? Now here you'll be able to see for cat what exactly it is. For cat, it is 0 1 0 1. Okay, so here I'm going to go ahead and write 0 1 0 1. right? So this basically becomes my query vectors, key vectors and value vectors, right? For cat. Similarly, the third one that we are basically going to compute is q of sat, k of sat, and v of sat. So in this case, we'll be able to see that I'm going to get 1, 1, 1, 1, right? So all this particular vectors is there. Perfect. Now, once we have actually done this, this is the first step, right? The first step is basically to get the token embedding. Then we create QKV by multiplying the embeddings by learned weight matrix. Right now it is still not learned. We have initialized it, but with the help of backpropagation, this will keep on getting learned. Okay. Now the third step that we are going to basically do is compute attention scores. We compute the attention scores. Okay. Now, as I told you, how do we compute the attention score? It is very simple. And over here, we have told queries help the model to decide which part of the sequence to focus on for each token. By calculating the dot product between a query and all the key vectors, the model assesses how much attention to give to each token. For doing this, we need to do a dot product of query vector and all key vectors. And that is how we calculate our attention scores. And why do we do that? It is very much simple to provide. See over here. Why do we do that? Because the model assesses how much attention to give to each token relative to the current token. So with relative to this particular token, that is how much importance I need to give to cat and sat tokens. Okay. And that is how we basically go ahead and compute our score. Okay. So for computing the score, right? So let's say for the word, if I go ahead and compute the score will be nothing but query of the and key of the. So first of all, we'll go ahead and compute this. So I know my query is nothing but 1010. And then if I want to multiply with k, right? K is also 1010. So I will probably take a transformation of this, right? Because if I really want to do the dot operation, if my q vector is like this 1010, I will probably do a dot operation by taking the transformation of this. And then only I'll be able to do the dot operation, right? So once I do this, I will be able to get the value as 2, right? So 1 multiplied by 1 plus 0 plus 1 plus 0, right? So finally you will be able to get 2. So for with respect to query of the and key of the, when I do the dot operation, I'm actually going to get the value of 2. Similarly, if I go ahead and calculate the score with respect to query of the and key of cat, right? If I do this particular dot operation, because we need to understand the context with respect to the other words also, right? And here is what I'm actually going to get it. So I'll be writing 1010 and I'm going to do a transform operation with what? What is key of cat? See, what is k of cat? It is nothing but 010, 0101. And this will be the transformed value. Now, if I try to go ahead and find out, I will be getting the output as 0, right? Similarly, if I go ahead and calculate score of query of the with respect to key of sat, right? Key vectors of sat. When we do the dot operation of q of the and key vectors of sat, here what we are going to get? Again, I'll go ahead and write 1010. And again, what is key of sat? It is nothing but 1, 1. This will be the transformed value. So here also we are going to get the value as 2, right? So this is how we compute the score values, right? And why we are doing this? Again, why we are doing this? It is very simple over here. It is basically to assess how much attention to give each token related to the current token. Okay. So we have got some kind of values over here. And this will actually help us to understand that how much context, how much focus should I really need to give with respect to the other token, with respect to the current token that I have actually considered, right? So here I have actually got some values scores, right? 202. Okay. Similarly, we go ahead and compute for the token cat. Now for the token cat, we need to do the same thing, right? We need to do the same thing. That is, go ahead and compute the score. Now the first score will be q of cat with respect to key of the, right? Now I have to probably consider whether there is a dependency, how much dependency I need to keep with respect to this, right? So here you'll be able to see that I will be able to compute it. Now here I will have 0101, right? And this time I'm going to do a transformed operation with what? A dot transformed operation with basically I need to transform this and do a dot operation, right? So here you'll be able to see if I do the computation, I'll be getting the value as 0. Similarly, if I go ahead and compute the score of qcat with kcat, right? So here it will be nothing but 0 1 0 1, which will be a dot operation of 0 1 0 1 transform, right? And here I'm actually going to get the value as 0. Then again, if I go ahead and compute this q of cat with k of sat, right? In short, I'm just doing a dot operation, right? So here I will be having 0 1 0 1 dot 1 1 1 1 transform, and again I'm going to get the value as 2. Okay, right? So just by seeing this word, you can just understand sat is important for cat. So that is the reason why I'm getting equal values for this particular score for cat with cat and cat with sat, right? This kind of dependency is definitely there. And I've definitely used identity matrix, but this all weight parameters will also get trained, right? Then similarly for the token sat, how do we go ahead and compute it? So we will go ahead and write the score, and here you'll be able to see q of sat, k of sat, right? So sorry, k of the. We need to do the dot operation with, first of all, the query vector of sat with the dot with the key vectors of the, right? So here I will be getting 1 comma 1 comma 1, which is my query vectors of sat, dot operation of 1 0 1 0, which is my transform operation, and here I'm going to get 2. Similarly, if I go ahead and compute this with sat and k of cat, I will be getting 2 over here. You can go ahead and do the computation, and then here you will be able to see k of sat. I'm also going to get a 4, right? So this is in turn the values that you will be able to see, right? And this is my third step. So initial step, what we do is that, first of all, we go ahead and compute. We take a token embeddings, then we do linear transformation and probably create this KQ wave vectors by initializing by learned weights matrices of W of Q, W of K, and W of V. In this scenario, I've just considered this as identity matrix. So let's consider it. Okay. Then I've shown you that how do we probably go ahead and compute this, right? When we do this particular dot operation. So I'll be getting the same values, and this is what I get it finally. Then we compute the attention scores, and this attention score is for a different purpose, just to how much focus I really need to give on the other tokens, right? So here I get all my token score values, right? Then my next step after this is something called as scaling. Okay, now what exactly is scaling? Okay, see, whatever scores that we are getting, right? Whatever score that we are getting over here, right? You'll be able to see that I'm getting some values like 224, right? 022 and 202, right? And you can clearly see that why this scaling needs to be done. Why we are specifically performing scaling. Okay. First of all, I'll just make you understand what does exactly this scaling mean. Okay. So scaling, what we do is that we take up this course and scale down by dividing the scores by the square root of dimensions of key vectors. Okay. So in our case, our dimension of the key vector is 4. So if I do square root of d of k, it is basically going to become 2. So guys, now let's understand why do we really need to consider scaling. Okay. So scaling, so let me just write it down. Scaling in the attention mechanism, is crucial to prevent the dot product from growing too large. Now when we say dot product between what? Dot product between the queries and key vectors that we have specifically done with respect to this, right? Now, why we need to prevent this dot product from growing too large? Okay, and in most of the research paper, it is basically given to ensure stable gradients during training. So let's go ahead and understand this with an example, okay? And if we don't scale, then what kind of problems we will be facing? And as you know that if decay basically means the dimension of the key vectors, if it keeps on getting large, here you'll be able to see that we will be facing two different kind of problems, okay? And as the dimension keeps on getting large, if we don't try to scale with this value, and if the dimension is getting larger and larger, right, we face two different types of problem. One is gradient exploding, right? Here you'll be able to see that during the back propagation, this gradient will become very, very large. And because of that, your training will not be stable, right? And the second one is something called as softmax saturation. So when I say softmax saturation, this basically means the softmax function has become saturated, where most of the attention weight is assigned to us just a single token, and for other tokens, the weight will be assigned to near to zero. The weight will be approximately equal to zero. So we'll discuss about it. Don't worry. I will try to explain you with an example. Okay. So two problems we are going to face over here. One is gradient exploding and the softmax saturation. Okay. Now let's see one example. Let's say that I am going to consider three vectors. One is Q. This is nothing but 2, 3, 4, 1. And let's say I have another vector K1, right? 1, 0, 1, 0. And another key vector that is nothing but 0, 1, 0, 1. Okay. Now let's, without scaling, let's do the dot product. Okay. When we do the dot product, so here what I will do, I will be using K along with K1 of transpose. So if I do the dot operation, how it will be 2 multiplied by 1 plus 3 multiplied by 0 plus 4 multiplied by 1, 4 multiplied by 0. So here overall I'm actually going to get this value. Okay. 1 multiplied by 0. It should not be 4 multiplied by 0, but 1 multiplied. 4 multiplied by 1 and 1 multiplied by 0. So overall, if you see 2 plus 4, it will be 6. Okay. And similarly, if I do the dot operation with the next key vector over here. So this will be 2 multiplied by 0, 3 multiplied by 1, 4 multiplied by 0, 1 multiplied by 1. Okay. And if you see over here, 0 plus 3 plus 0 plus 1, it is nothing but 4. So with respect to this two dot operation, initially my key values were this much. Okay. Key vectors were this much, but now after the dot operation, I'm getting 6 and 4. Okay. Now, after this scaling, let's say that I'm going to apply a softmax, because that is what happens here also. So first of all, we need to apply scaling, and then after that we'll apply a softmax activation function to get the final contextual embedding. Okay, that is what happens in the next step. So let's say here I have got two scores. One is the score of 6, the other one is the score of 4. Okay. Now let me do one thing. Here we are not going to apply any scaling. I'll just go ahead and write. You'll understand the problem, what problem you are going to face. Scaling not applied. So if I don't apply the scaling, you'll be able to see over here what? I will just go ahead and apply my softmax. Now softmax will get applied to both this number 6, 4. Okay. And here when we are specifically applying the softmax, okay. So here you'll be able to see that if you remember about the softmax formula, it is nothing but e, let's say e to the power of 6 divided by e to the power of 6 plus e to the power of 4, okay, comma e to the power of 4 divided by e to the power of 6 plus e to the power of 4 when we specifically apply on this two, okay. And here, if I just go ahead and see to this, so let's say e to the power of 6, and here I will take e to the power of 6 as common, and I'll write 1 plus e to the power of minus 2. This is how we can represent it. Similarly, if I go ahead and write e to the power of 4, and if I take common as e to the power of 4, I'm going to get e to the power of 2 plus 1. Okay. So from here, if we do the forward calculation, since we are applying in Softmax activation function, this will be nothing but it will be, let me do one thing. Let me just go ahead and write 1 divided by e to the power of 6. E to the power of 6 will go off. So it will be e to the power of 1 plus e to the power of minus 2, comma, and this will be 1 plus e to the power of 2 plus 1, right? This e to the power of 4, e to the power of 4 will get deducted. Now, once we are calculating this, here you will be able to see that the final output, if I do the calculation with the help of calculator, it is nothing but it is approximately equal to 0.88.12. Okay. So what has happened is that when we applied this Softmax activation function on a score of 6,4, which we got as a product of query vectors with the key one vector of this specific word, of any word. So here we had this key one vector, here we had this key two vectors, right? And when we do this, when we did this dot product, we got 6,4, we calculated the score. Here we did not apply any scaling. And finally, you could see that we could get a Softmax. When we applied a Softmax activation function, here you got a value of 0.88 and 0.12. Okay. Now, what does this value basically mean? First of all, this value actually means that most of the attention weight, okay, is assigned to the first key vector, right? Because the value is higher. This is higher than this, right? And very little to the second vector. Okay. Now let's understand what does this sentence mean. Most of the attention weight is assigned to to the first key vector, that is 0.88, and very little to the second vector. Okay. And let's understand. See, one of the property I think you should be knowing if you have knowledge of deep learning, right? So one of the property of Softmax is that whenever we apply a Softmax to two numbers, right? Two scores are there. Here you can see the difference between this score is very less, 6,4. But with respect to the output, here you are able to see that there is a huge difference. 0.88 I'm getting to the score 6 and 0.12 I'm getting to the score 4, right? And similarly, if I try to apply a Softmax activation function on a number like 10,1, now in this case 10,1, you'll be seeing that there is a huge difference, right? And these values are basically coming from the dot product of Q and K, right? And here you can see that I have not applied scaling, right? So one of the property, if I do not apply scaling, whenever I try to find out the Softmax for this, again, if I try to find out the output, you'll be able to see that one value will be like 0.99 and one value will be like 0.01. Now in this scenario, again, this value is very high, this value is very less, okay? You should understand all the scores will be specifically used for updating that particular weights that we are using, right? The weights like W of Q, W of K, W of V. Now when we are doing back propagation, right, this small value, just imagine when this small score comes into picture, obviously we are going to face a problem of Softmax saturation, right? So there will be one problem, that Softmax saturation, where my gradient is not going to get updated more because the value that I'm actually going to get is becoming very small. And during the back propagation, I can also say this term as vanishing gradient problem, right? Vanishing gradient problem, where my weights are not getting updated. vanishing gradient problem. So this is the property with respect to Softmax. See, right now, I did not do any scaling and I got this kind of value like 0.88, 0.12. Even though my value of scores was 6,4, not much difference, hardly a difference of 2. Similarly, if I do a dot product of query and key vectors, if I'm getting a very high value, over here, if I apply the Softmax activation function, just try to apply the Softmax activation function, you'll be able to see that I'll be getting a very high value at one of the vector and the other value will be very, very small, right? So this scenario we usually face when continuously you'll be able to see when your dot product that you specifically do is coming as a large values. Okay. Now let me do one thing. Let me just show this by using or by scaling this value. Okay. So now I will just go ahead and write with scaling. With scaling, we'll try to apply the Softmax activation function. Now here you can see with scaling, first of all, I will just go ahead and compute my scaled dot product. Okay. You know that compute scaled dot products, right? Now, obviously, you know my score 1, right? My score 1 was 6 and 4, right? Now for this 6 and 4, what we do, first of all, if I really want to scale it, right, I need to divide it by root of dk, right? I need to divide this number by root of dk. So I will take each and every number, I'll divide by root of dk. Root of dk is nothing but, it is root of 4, which is nothing but root of 2. So if I divide 6 by 2 and 4 by 2, I'm going to get what? 3, 2. Understand, my scores were initially 6, 4, but now I have scaled it with this value, that is root of dk, and then I'm actually getting 3, 2. Now if I go ahead and apply Softmax on 3, 2, you just go ahead and do this calculation, how much you will be getting. Okay. So again, I will do the calculation over here. E to the power of 3, e to the power of 3 plus e to the power of 2, comma, e to the power of 3, sorry, e to the power of 2. And this is e to the power of 3 plus e to the power of 2. Similarly, if I go ahead and probably do this computation, okay, you can take what all commons you specifically want. Let's say here I'm going to take a common of e to the power of 3 divided by e to the power of 3. I will take it as common. This will be 1 plus e to the power of minus 1, okay, comma, e to the power of 2, e to the power of 2, I'll take a common. Then here I'll write e to the power of 1 plus 1, okay, and this will get deducted, this will get deducted. So finally, what output I'll be getting if I do the computation, it is nothing but 0.73, 0.27, right? Now, before, when we did not apply the scaling, you could see that I'm getting a value as 0.88, 0.12. The difference is very huge. But now here you can see there is a less difference. So when we are now back propagating, right, we will not face that problem of vanishing gradient problem, right? And here you'll be able to see the output, or this is also called as an attention weights. This is my attention weights. This attention weights, let me write a point over here. Here, the attention weights, here the attention weights are more balanced compared to the unscaled case. So if we are scaling, now we are getting a proper balance. Before, the difference was huge. I know here also you can see the difference is there, but at least in the back propagation with respect to the other vector that we have, right? And when we try to update the weights, at least we won't face the vanishing gradient problem. Okay. So this is the most important thing, right? And because of this, if I just try to write down the summary for you, okay, let me just note down all the summaries point that I really want to specify over here. Because of this, there are two important things that you need to take a note of. Okay. So the first thing is that here you are stabilizing you are stabilizing the training. Scaling prevents extremely large dot products, which helps in stabilizing the gradient during backpropagation, making the training process more stable and efficient. And second, you are preventing saturation. By scaling the dot product, the Softmax produces more balanced attention weights. Now, there is a more balanced attention weight. This token is also having some importance. This token is also having some kind of importance, right? Before, even though we give any kind of values over here, the gap was very high when we were trying to create the Softmax. And that is what is basically like creating a stable gradient, right? We specifically divide by this number. Now, you may be thinking, Krish, how did we come for this particular number, right? Why we are specifically dividing by root of d of k? So guys, for this, there is a one simple research with respect to variance. Okay. Whenever we do the dot product, as we keep on increasing the dimension, the dot product variance will also keep on increasing. Okay. So as this was keeping, and there's a research for this, guys, as this keeps on increasing, okay, here you will be able to see that if we divide by root of dk, this is making sure that even though the dimension increases, even the dimension is 2, 3, right, the variance for that particular dot product will be almost same. That is what this specific number is all about, right? And this is a small research in variance. I just have mentioned it so that you can refer it whenever you want. But I think for our understanding, this much is more than sufficient. Okay. So because of the scaling, one more point that I can specify over here is that scaling ensures the dot product are always kept within a range that allows Softmax activation function to operate effectively, providing a more balanced distribution. Okay. So if I go again back with respect to all the steps, so my fourth step was scaling. And after scaling, we will just try to understand what is the next step. Okay. But here I've shown you multiple examples with respect to scaling, right? So if I just go ahead and show you what all things we discussed till now. First of all, we go ahead and, do the token embedding. And then with respect to the token embedding, we do the linear transformation where we are going to find out three important vectors: query, key, and value pairs. I've told you about the discussion with query, key, value pairs, why it is important. Then we go ahead and compute this. Then we compute the attention scores. And this attention scores also play a very important role. Then we probably do the scaling part with respect to this. Okay. Now, once this scaling is done, right? Once we specifically do the scaling, then we calculated the weighted sum of all the values. Okay. That is what the next step is all about, right? And I know this may be somewhat confusing, but it is always good that we try to understand things. Okay. So let me go back to my previous problem statement here. If you remember, we had calculated the scores, right? All the scores, right? For compute attention scores. For the score of query of the with respect to key of the was 202. Like the scores we have actually computed, right? So let me do one thing. Let me just go ahead and apply Softmax. So before that, we will do the scaling, okay? And then we will compute. And I will take only one word for this, okay? Or one word. I'll just try to show you with respect to one word, and then you should be able to understand. So the fourth step that we are specifically going to do is nothing but scaling. I've shown you one example of scaling. So scaling, what we will do, we will try to divide by root of d of k, okay? In this case, it is 4. So this will basically become 2, right? Root of 4, which will become 2. Right? Then we are just going to calculate our scaled score. So if I go ahead and calculate with the query of the with key of the, right? We had this value initially 2 and we are dividing this by 2. So I'm going to get 1, right? Similarly, if I go ahead and calculate our scaled score with q of the and k of cat. So here we are just going to divide by number 0 by 2, which is equal to 0. Then I have my scaled score. Then this is nothing but q of the comma k of sat. So initially this was 2. So I'm going to divide by 2, which is nothing but 1. Now, once I do this division, you'll be able to see that again, this value has got decreased, right? So similarly, all the scaling will be done. Similarly, you'll be seeing that scaling will be done. Similarly, scaling will be done for all other tokens. Perfect, right? Now, after this, as I've already told you, the next operation will be specifically apply Softmax. Now, when I apply Softmax here, you'll be able to see that, and this Softmax will be applied to the scores that we have actually got, the scale scores. And then whenever we apply the Softmax, we basically create our attention weights. So the attention weights is what we get. And this attention weights is nothing but so for the word, the attention weight will be Softmax applied on my values like 1, 0, 1. So here, once I apply this Softmax, you can go ahead and check it out. I've done the calculation. It is nothing but 0.4223, 0.1554, 0.4223. Okay. So here, initially, your value was this, right? With respect to the word, what was your initial vectors? See this? Your initial vectors was 1010. Okay. 1010. Okay. I missed out one. Oh no, we got it exactly right. So 1010 was your initial vectors. And now I'm able to get this as my contextual embedding vectors. Similarly, when I go ahead and calculate for the attention weights of cat. So this was the cat, right? Here, if I apply the Softmax activation function, and the Softmax activation function is applied on 0, 2, 2. Then I'm going to get 0.1554, 0.4223, and 0.4223. Now, whatever vectors we are getting, this is considering the other vectors in context. Okay. Similarly, once we go ahead and calculate the attention weights for SAT word. So again, we have to go ahead and pass our Softmax, and this will go to our 2, 2, 4. Okay. And here we are specifically going to get 0.2119, 0.2119, and this is 0.562, right? So this is how we go ahead and apply the Softmax activation function, and we get the attention weights. Okay. Now finally, see, this is just our attention weights. Like, what are the attention weights with respect to all the other values? But you remember, right? Initially, we gave a 4-dimension vectors, and finally, the output also should be a 4-dimension vector. So the final step that we are specifically doing is weighted sum of values. Now, in the weighted sum of values, what we do is that we multiply the attention weights by the corresponding value vector, because somewhere that value vector needs to be used, right? Value vectors to get the final output. So for the token, right? If I want to go ahead and calculate the weighted sum, so I will just go ahead and write the output of the will be nothing but it will be, what is the attention weight? 0.4223. So first one, I'm getting 0.4223. This will be multiplied by value vector of the, right? Then the attention weight of cat, right? We will just go ahead and do this. See, the output, see, the vector needs to be converted into some other vector, right? And it should be converted with respect to the context of cat and sat. So attention weight of cat. So what we are going to do, we are going to basically use the next weight, that is 0.1554. So here I will go ahead and write 0.1554, and this much attention needs to be given to the value vector of cat. Similarly, the last one is 0.4223. This much attention needs to be given to the value of sat, right? Value vector of sat. So 0.4223, right? Similarly, once I probably go ahead and do the forward calculation. So here you'll be able to see I will use 4223. Value of the is what? So if you remember, what did we consider as the value of the, if you see this, so this is my K value. So value is nothing but the initial value that we have used, embeddings, right? So let's see the value. So for the, it is 1010, for this it is 0101, and for SAT it is 1111. Okay, so let's go ahead and write this. I'll do the calculation over here. I know there are many steps, guys, but please focus. I'm solving it completely step by step. 1010, then we will we will add 0.1554 multiplied by V of cat, right? So V of cat is nothing but 0101. Then you have 0.4223 1111. Okay. So now once we do this dot product, what values we are going to get over here? Very simple. Just go ahead and do the computation. So first of all, when we do this particular dot product over here, so the further calculation, once we do this particular dot operation here, we are going to get 0.4223, then again 0.4223, right? This will be my first vector. Then I have this vector 0.1554. Sorry, it will be 0. Initially it will be 0 because we are doing a dot operation with 0. Then I have 0.1554, then again 0, then 0.1554. Okay. And similarly here I will be having 0.4223, 0.4223, 0.4223, 0.4223. Okay. Done. So once I get this, it is nothing but finally I'll be able to get 1.2669 and if I just do the plus operation with respect to all the numbers, okay, 0.49, 1.2669. You can validate it if I'm doing all the computation right. If not, you can let me know in the comment section. Okay, so this is basically my output. So initially you'll be able to see that when I gave the keyword, which was having an embedding vector of 1010, after passing through the self attention, it is giving us this keyword, that is nothing, this vector, that is contextual vector 1.2269, 0.999, 1.2669, 0.9999. Okay, so this is what is my contextual vector. Okay, contextual vector. Here what we did, first we calculated our q, k, v values vectors. For this we initialized w of q, w of k, w of v vectors, and again this will be trained. Then after this we went and calculated our attention score. After calculating attention score, we scaled the value. Then after doing this, we passed it through an Softmax activation function. And finally, we calculated the weighted sum of values. And how do we calculate this? It is very simple. After performing the Softmax, whatever value we get, we have to multiply with V, right? And that is how we specifically get all these values. Okay. I hope you are able to understand this, and similarly for token, cat and all, we can also do the calculation. I will leave up to you like how you can probably do the calculation, but again for token cat you can follow the same mechanism. So here you have 0.1554, then you multiply it by the vector of value of the, then value vectors of the, then you have the second one 0.4223 multiplied with the value of the, and similarly when you do this you will be able to get all these things, right? So this in short was your entire self attention, step by step what all things we did, how the calculation was, everything I have explained you. This entire weights will be trained. These are trained learned weights. I will say it as learned weights, and we have to make it learn based on the back propagation, like how we specifically do for other neural networks. Hello guys, so we are going to continue the discussion with respect to our transformers. Already in our previous video we have discussed till self attention, and we have also noted down all the steps that we specifically use in self-attention. So first of all, we go ahead and calculate our query key and value vector. And this is from a learned weights, that is W of Q, W of K, and W of V. Then we calculate the attention score. Then we calculate our scale scores. After doing that, we apply a softmax activation function, and finally we calculate the weighted sum of the values. And this is just done by multiplying with the vector V. Okay. So overall, you'll be able to see that initially when we are giving some kind of embedding vectors, we should be able to get some kind of contextual vectors over here, right? And this contextual vector is based on the context and the dependency of the other words that are present in that sentence. Okay. So this is one of the blog that has some amazing representation diagram, and the URL specifically, if I probably go ahead and talk about the URL, I will just also show you the URL over here. Again, I really want to give the credits. So it is nothing but Jala Almar. So this amazing diagrams he has basically covered with the working of the entire transformer. So you can definitely check it out and you can have a look onto this. Okay. Now my idea is very much simple over here. What I really want to do is that I want to again show with the help of diagram what all things we did, right? So here you can see this is one of the diagram, and here in this video I'm also going to discuss about something called as multi-head attention. Okay, so this we are going to discuss about it, multi-head attention. Okay, now initially I have my words over here. Let's say this is my word 1. What is the word? Like this can be this can be cat, right? This will be first, all my vectors will be available over here. We are multiplying, or we are doing a dot operation with W of key, and this is how we get our query vectors, we get our key vectors. And remember, for each and every word that I have, I get a separate query and key value vectors, right? And similarly, separate value vectors. We separately get all these things, right? And after we get this, what we do, we first of all do a multiplication operation with the query and the key, right? Then we divide it by root of dk, where we are specifically doing scaling. Then we apply a softmax activation function, and finally we do a dot operation with our value vector. And that is how we get our z value, which is nothing but it is my attention, self attention for the word the, right? The vectors that we are specifically getting. Now till here, I think everybody has followed this, and step by step, I've actually explained it, right? And we can actually say this one as our attention head. Attention head. Now the idea with multi-head attention, what exactly is that? We'll have a self-attention with multiple heads. Multi-heads. Okay. Now this is fine. Here you can see I got one kind of vector for the, right? Similarly, can't you think that I can probably go ahead and create multiple attention heads for the same words, right? So here you can see I have taken thinking machine as an example over here. So this is my embedding vectors. Initially, we went and we initialized some other weights like W of O of Q, W of O of K, W of O of V, right? And we calculated this query Q of O, K of O, and V of O, right? Similarly, and after this, what will happen is that again, that same method, it will probably go to it'll calculate the score, then it will go to the softmax, then we multiply by V, and finally we get our attention head, right? Or we get our final vectors after performing all this particular operation, right? So we get our contextual vectors. Here we get it, right? Now these vectors may probably take up dependencies with respect to other words. Let's say in this example, thinking machine is there. Or I can also take another example, this cat, sat, mat. Okay, if this 3 is there, right? Now finally you'll be able to see whatever vectors I get over here. This will be with respect to dependencies on this and this, right? Let's consider that it has captured with respect to this and with respect to this. and it has probably given me this. Similarly, it can go ahead and create another attention head where it will be able to capture some more words importance, right? And for this, they will initialize another vectors, another weights like W1 of Q, W1 of K, W1 of V. And similarly, they will be getting vectors like Q1, K1 and V1. So whatever vectors we are getting out of this may be different than this may be different than this. Here, some more other context importance is basically getting captured. Here, some more other context, the importance is basically getting captured. So this can actually become my Z0. This can become my Z1. So similarly, I can go ahead and create multiple attention heads, so that what will be the main aim of this particular multiple attention heads? It will expand the model's ability to focus on different positions. So here I will go ahead and write, it expands the model's ability to focus on different position of words or different position of tokens. This is what it says. Yeah. So here you can probably see, right? Z0 may contain a little bit more information of every other encoding, but it can be dominated by one word like sat, right? Here, Z0 may be like that. Z1 may be like, it may focus more on different words. It can be dominated by word like mat. So if we have all this kind of combination, right, then what will happen is that we will be able to get more and more information to our models, right? So here, this attention layer provides multiple representation subspaces, okay? And in case of multi-head attention, we have not only one, but multiple set of key value pairs. Right? And each of this set is randomly initialized initially. Then after training, each set is used to project the input embeddings into a different representational subspace, okay? That basically means it will take a vector and it will try to convert them. So overall, you'll be able to see that by using this, we may get this kind of diagram. See, so here, with a different set of QKV, we will be able to get this attention Z0. With a different set of QKV, and along with that, obviously W of K, W of Q, W of V. This weights will be also different. Similarly, we can go ahead and calculate this attention, which will capture other importance thing in the token, right, with respect to the positional encoding. And then here you will be able to see different captures, different outputs, right? So this is the entire information about multi-head attention. So here we are just not focusing on providing one set of vectors with respect to this, but we'll have multiple set of vectors, and each of the other vectors that we are getting, right, which we also call it as attention head, it will have importance with respect to other tokens that is available over here in the sentence. Okay. So yeah, this was it about multi-head attention. The concept is very similar. Whatever steps we are doing, instead of just getting one attention head, we will try to get multiple attention head, wherein we will try to train it with multiple that is queries key value pairs by initializing W1 of Q, W1 of K, W1 of V, right? Weights of Q, K and V. And as many number of attention head will be there, that many number of weights can be parallelly done, right? So this was more about the multi-attention head. So multi-head attention, and yeah, in the next video, now here you can see that what all things we have specifically discussed, right? If I go up, oh my God, I've written so many things for you all. So here you can see after performing this self-attention, I need to provide all this information to my feed forward neural network, right? But here you can probably see now how my diagram will change by multi-head attention. Once I give how, right? After this self-attention, I will be able to get like this multiple heads of vectors, right? So this will be my attention head 1, 0, attention head 1, attention head 2, attention head 3, attention head 4, attention head 5, right? Similarly, for this word, I may get other attentions. Now, all this I need to pass it to my feed forward neural network. So obviously the feed forward neural network will consider this as just one encoding. So we need to combine this, and that is what we are going to see, that how we are just going to pass all these things to a feed forward neural network and how the forward and the backward propagation is going to take place. So guys, we are going to continue the discussion with respect to our transformers. So already inside an encoder, we have discussed how the self-attention exactly works. And again, in our previous video, we have spoken about query, key, value vectors, and then how a score is basically calculated, attention score, how a softmax activation function is calculated, how a softmax activation function is applied, everything we discussed, right? Now, after we get the vectors, now see in this scenario, right, when I spoken about multi-head attention, for every word, I'll be getting like attention head 1. So I'll be writing Z1, Z2, Z3, right? Z4, Z5, and so much, like it can be 7 to 8 Zs, right? So if I say there are 8 attention head, I'll be getting 8 Z1, Z2, Z3, Z4s, a kind of vectors by passing this specific word. Now the next step will be that I need to pass all this to my feed forward neural network, so that I'll be able to do the further steps, right, inside this particular encoder. Now the problem is that before what we had drawn in the diagram here, I said that, hey, we are just passing one word, I'll be getting one vectors, right? But here we are getting multiple vectors. So before we pass through the feed forward neural network, we need to combine all the specific vectors and send it to the feed forward neural network, and then probably do the forward and the backward propagation. So the feed forward neural network is expecting a single matrix. So we need to find out a way how we can condense all this attention head into a single matrix along with some a single weights itself, and probably do the entire task. So here you'll be able to see right now I have multiple attentions like this: attention head 0, attention head 1 till 7, and here I have all the values, right? I have over here, I have over here, I have over here. All these values are specifically there. Okay. And when I say values, here you have this QKV, here you have separate QKV, right? Here also you have a separate QKV. Now the problem starts at how do we combine all these things before we forward it to the feed forward neural network. So for that, here you can see an amazing diagram. We concatenate all the attention head like this. So Z0, Z1, Z2, Z3, Z4, Z5, Z6, Z7. We are considering that there is a 7 head attention. Okay. So we combine all of them. We do a dot product with W of 0. So this will be my W of 0, where I will be initializing a new weight for my feed forward neural network. Feed forward neural network. And after this, we go ahead and calculate our final Z. Okay. So after this, whatever Z we are probably getting over here, this will be a single Z. This will be my another Z. This will be my another Z, right? And this is what we are going to pass it to our next encoder, right? So all the multiple attention head, we are just going to combine it together to make sure that we capture all the specific importance. We give it to the feed forward neural network, and along with this, we train a specific weight itself. And this is just for one word. Just imagine the one word that I've given, the, right? Or it can be cat. So from this cat, by using self-attention, I've created so many different heads, right? By using, and all these heads will have a separate key value vectors, everything will be separate, right? Then along with this, I'm taking a weight, forwarding it to the feed forward neural network, then we'll train it to finally get our output that is called as Z. Okay. And this is pretty much all to the multi-head self-attention. It is a handful of matrices. Okay. And you'll be able to do it probably in this way. Overall, if you really want to check one more amazing diagram again from the same blog, I will also draw it for you over here. And this is how the things happen, right? From the entire self-attention till the feed forward neural network. Okay. So here you can see that from this part to this part, right? From here or from here, the entire feed forward neural network actually takes place. So here is your two words that I've given, thinking machines. Then for all these words, you have this separate weights, so that we'll be able to get our separate Q, K and V vectors. And finally you get your Z0. This is for the attention head 1. Then again, for this, you have a separate vectors. For this, you have a separate vectors, right? And for all the attention head, you will be having a separate q queries key value vectors itself. And finally, you get this entire weights and you train it on your feed forward neural network to finally get your Z. So this was my initial vector. This is what is my final vector that we are specifically getting. Okay. So this is our input sentence. We embed each word, split into 8 heads. We multiply X or R with weight matrices. You calculate the attention using the resulting matrix. Then you concatenate the result of Z matrices and multiply with the weight matrix W2 to produce the output of the layer. So with respect to one word, I will be able to get this. Like let's say thinking is there, then I'll be able to get this vector. Machine is there, I'll be able to get this vector, right? So this overall explains about the entire attention head. The reason of having multiple attention is that I really want to show you with one practical example. Okay. So here you can see I have over here one visualization diagram. I'll be giving this link in the resources section. Okay. Here you'll be able to see that with respect to every word, right? And okay, this will not be a good diagram. So here you can see I have multiple attention. So this can be my attention head 1, attention 2 head, attention 3 head. If I click on each and every attention, you'll be able to see that every attention has a different importance word, right? It is trying to capture much importance with respect to all the words that we have. So if I go ahead and click, this is my other attention. This can be my other attention. This can be other attention head. You know, it shows the importance of each and every word. So if I just go and highlight over here, see, lay is basically very much highly dependent on, right? So these vectors that will be defining this lay will be specifically on, right? And similarly, if I go ahead and click on other vectors, let's say on is there, cat is there. See, mat is there, separator is there. Cat and mat are highly correlated, right? Correlated basically means there is a huge context dependency on that, right? So this actually gives an idea. And here also you can go ahead and check it out with respect to sentence to A, sentence A to B. Let's say the cat sat on the mat, the cat lay on the rug. If I want to probably see, is there any dependencies? So cat is having a dependency on cat. If I probably consider sentence A to A, cat sat on the mat. So see, on sat is the first word that it is having a dependency on. So it's the main idea of self-attention is to get this all, right? And with respect to different head, we will be able to get this. Some more examples, which I will be putting it here, right? You can probably check it out. So this is one attention head, which you will be able to see. So here I have a sentence. The animal did cross the street because it was too tired. Didn't cross the street, it was too tired. So here you can see, when I highlight on it, it is dependent on street, tired, and animal, right? So some more words are specifically here. Similarly, if I go ahead and see with respect to other attention head, right? Once we calculate, you'll also be able to see this kind of context. So here it is dependent on the animal with different color, cross, right? So multiple attention head basically means you are able to get information from multiple heads itself with respect to the dependency on all the other words. So this was it, where we have specifically discussed about multi-head attention. We have discussed about self-attention and all. Still, there are many more videos that are going to come. Couple of videos. One is positional encoding, which we are going to discuss. And after that, we will also go ahead and discuss about the entire transformer architecture, because still we are just understanding some of the components in transformer, right? Hello guys, so we are going to continue the discussion with respect to transformers. Until now we have discussed so many things, that is self-attention layer. We have discussed about what is multi-head attentions, what all operation specifically happens inside the self-attention layer itself. We have actually discussed. Okay. Now in this video, we are going to discuss about a very important topic, which is called as positional encoding. That is nothing but representing order of sequence. Okay. Now see, this order of sequence is a very important thing. Okay. One of the major advantage of using transformer is that, okay, the major advantage, all these tokens, right? All these words tokens, it can process, it can be processed parallelly, right? This is the most important advantage, because at a time I can just directly go ahead and pass my x1, x2 word, and all this operation that specifically happens in the self-attention layer, it will just happen parallelly, right? And if I consider, because of this advantage, there is also a specific drawback. So now if I talk about the drawback, because of this advantage, it lacks the sequential structure of the words. Now, what does that basically mean, right? Now, the sequential structure basically means the order, right? Obviously, since all the words are specifically taken by the self-attention layer in a parallel mode, all the word tokens are taken all at once and all the processing is basically happening, it will not have any idea whether X1 word has come first or X2 word has come first, right? Let's say I take an example over here, right? I say, hey, lion eats tiger, okay? Or I can basically say lion kills tiger, okay? So we can take this example. So this is just one sentence. The other sentence can be tiger kills lion. Now, because of this ordering of the sentence, of sentence 1 and 2, the meaning of the sentence completely changes, right? Anyhow, in both these sentences, all the three words are basically considered. And at the end of the day, if I pass this through self-attention layer, and since right now my self-attention layer is also not taking care of the ordering part, both this sentence will be returned with the same vectors, right? With respect to all the words. But as you all know, this entire sentence is completely different because of the ordering of the word. So this is what right now my self-attention layer or this entire transformer architecture is missing, right? It is missing this information. So in order to prevent this, what we specifically do is that we use a concept of positional encoding, and this positional encoding will be responsible in representing the order of a sequence, okay? And that is what we are going to learn about. Because without this positional encoding, it will not know which word is probably coming first, okay? So the concept is very simple. What we will do is that, according to the research paper of attention is all you need, right? Attention is all you need. So what they have actually done is that they will see if this is my embedding vector, right? For this particular word, Similarly, we will go ahead and create another one vector, this vector, and we will see how we can generate this particular vector. And this vector will be nothing but, it will be the positional encoded vector. This is nothing but the positional encoded vector. And this positional encoded vector will be added with this vector. Similarly, this positional encoded vector will be added with this vector, and this vector will be responsible in telling which words are in which position exactly, okay? And that is what is the entire idea over it, right? See, there are multiple ways how we can fix this particular problem. One of the way is that, why not with this embedding vectors that we are passing, let's say over here I've just taken 3 dimension. Why not just add one more dimension and probably talk about the position of the words that are coming. Let's say for the first sentence, tiger comes first. So this position will be 1. Then the second vectors that we are specifically giving, this position will be 2 along with the vectors that we are giving. And the third word basically is about lion. Let's say that we are giving one more word over here with the third index, right? So once I'm sending this information, here we are giving some kind of position, right? But do you think right now for a smaller text, it is fine. But let's say if I have a book or if I have a journal or if I have a novel, right? Here, there may be more than 1 lakh words. Now, if there is a more than 1 lakh words, obviously we are not limiting how many number of positions we'll keep on writing, right? And when we have so many number of words, and just imagine we are trying to add a vector with such a big number. So this usually causes a problem while we are doing the back propagation while updating weights. And if we consider huge data, right, there is no limit of that particular word. So that basically means the right now with respect to the position, it is unbounded. this position can have any number of words, right? So this is one of the problem, and we cannot directly use with this specific position. You may also say, hey, we can probably apply some kind of mathematical rule and we can try to replace it. But if we go according to the research paper, that is attention is all you need. Here, the idea is very simple. Here, we will try to add a positional encoded vector, which will be of the same size. And then we will try to add this particular vector to this embedding vector itself, right? And that will actually give the position information with respect to the word that comes in the sentence. But now the question comes, right? How do we probably create this positional encoding vectors? Okay. So for this, there are two different ways, and out of which we will be discussing one of the way which is even spoken in the research paper, which is written in the research paper. So types of positional encoding. Okay. So first one is nothing but sinusoidal position encoding. Sinusoidal position encoding. The second one is something called as learned positional encoding. Okay. So out of this two, okay, I will give a detailed idea about what exactly is sinusoidal positional encoding. We will try to understand this. Okay. And sinusoidal, so let's go with the first one. That is nothing but sinusoidal positional encoding. Again, what exactly this is? This is basically a technique of creating that positional encoding vectors. So here it uses sine and cosine function. Sine and cosine functions of different frequencies. We will try to understand what exactly it is. Okay. Of different frequencies to create positional encodings, and we'll solve this entirely with a good example also. Okay. And now, because of this positional encoding, because of this positional, will not have this particular problem also, like it will not be like unlimited, because this sinusoidal encoding, all the values will be ranging between -1 to +1, and at any point of time with respect to any number of vectors, okay, you'll be able to see that either we'll be getting the values between -1 to +1. Okay. So let's see this, how this exactly works, and then we'll try to understand with a basic example. First of all, in order to compute the sinusoidal position encodings, the formula is very simple. Okay. And here what we are doing, basically, whatever vectors we really want to create, right? Positional embedding vectors. All these values, let's say if I have a 4-dimension, all these values will be replaced, right? All these values based on the position of the words will be replaced by this formula. So this is positional encoding. That is nothing but position, comma 2 of I. It is nothing but sine position divided by 10,000 to the power of 2 of I d of model. We will try to understand each and everything. Okay. This is for the sinusoidal sine function. One more positional encoding that we will try to calculate is nothing but position of 2 of I plus 1. 2 of I plus 1. Yeah. This is nothing but cosine of same formula, that is position of 10,000 squared 2 of I divided by d of model. Right. So this is the formula. Now here, let us break down this particular formula, because see, at the end of the day, we need to create this positional embedding vectors in such a way that the dimensions that we specifically have with respect to the embedding vector, the same dimension it should happen. So here we will go ahead and write where P is equal to, where POS is equal to is nothing but it is the position. Okay. I is the dimension. Okay. D of model is the, let me just clearly write this down. Okay. So here I will just go ahead and write where POS is the position. Everything will make sense once I solve a specific problem and show it to you. And then here I is the dimension. Okay. And then you have this D of model. It is the dimensionality of the embeddings. Okay. Now what exactly this is and how we will go ahead and compute it, I will just show you this with a specific example. Okay. Let's say here I have an example which says the cat sat. Okay. First of all, we'll convert this into vectors. Okay. So let's say that this is my the is represented by a vector like this 0.1, 0.2. I'm just initializing 0.3, 0.4. Okay. Similarly, I have this cat is represented by 0.5, 0.6, 0.7, 0.8. Okay. And then you have this sat is nothing but it is 0.9, 1.0, 1.1, 1.0. So this is the embedding vectors that we have. Now we will go ahead and create the positional encodings for this, because before giving it to the self attention layer, the same dimension, this is just a 4-dimension. So this entirely is like 4-dimension for each and every word. Similarly, we have to go ahead and create our positional encoding with the same 4-dimension. And we are going to specifically use this technique, which is called as positional encoding with the sinusoidal learning. Okay. So here, what we'll do, again, we'll go ahead and probably use the formula. Okay. With respect to the positional encoding. So here I'll write PE. Let me use another color. So here I will just go ahead and write PE with respect to POS, comma 2 of I is nothing but sine of POS 10,000 square I of D of model. Okay, the same formula. And here I'm just going to write PE, that is positional encoding of POS comma 2I plus 1 is equal to cos of POS 10,000 2 of I divided by D of model. Okay, perfect. Now understand over here. Okay, I have to generate 4 positional encoding vectors. Okay, so here for our example, okay, D of model basically means what? Dimension of model. So dimension of model is 4, right? 4 over here. So I will just go ahead and write for position pos is equal to 0 for this position. For this position, how do I place a value? Okay, so for this I will go ahead and calculate PE. My position is 0, comma, what is I over here? What is I? 2I comma 1, 2I plus 1. Okay, so for the first word you'll be able to see, right? For the first word I have to represent this into 4 positional encodings, right? So I will iterate through this specific I, right? So here what I will say, for position 0, if I want to calculate the positional encoding for 0 comma 0, it is nothing but sine of 0 divided by whatever is there, 10,000 square, square 2 of I. So I is 0 over here, right? So this is 0, right? So obviously this will entirely become 0. That is nothing but 0 itself. So here I will just go ahead and write 10 to the power of 0, right? Because I is 0 divided by D of model, again it is nothing but 4. So this entirely sine of 0 it will become, right? So here I'm actually going to get 0 itself. Then similarly, if I go ahead and say positional encoding for 0 position, but first ith, like 1 ith position, okay? Ith position. How many ith position I have to really do? It is 0, 1, 2, 3, right? So for the first, again, I will go ahead and compute sine 0 divided by 0 divided by anything over here will be 0. Sine of 0, again it will be 0. Sorry, it should not be sine of 0. Just a second. It should be cos. Because for every position, you'll be able to see that I will be applying this position and then I will be applying this position, right? So here you will be able to see with PE, with positional encoding with 0, 1, okay, is nothing but cos of whatever cos function we are specifically writing. Position is nothing but 0. 0 divided by anything will be 0. So cos 0 is nothing but 1, okay. Similarly, I will go ahead and compute for positional encoding for 0, 2. Now 0, 2, again I will be using sine, okay. See, you'll be able to see that if I have two embeddings, like if I have this 4 dimensions, whenever I apply a sinusoidal wave, right, like this, a sinusoidal wave looks something like this, and the cosine waves look something like this. So for each vector, we have to probably go ahead and find out the sinusoidal wave, sinusoidal values for that, and for the cosine values for that. That basically means if I want to find out the positional encoding for this 4 dimension vectors, here this one will basically be calculated as a combination of 2. So let's say this is my first combination, this is my second combination. That is the reason we are using this formula. This combination will be calculated, the first one will be calculated with this formula, and the second one will be calculated with this formula. And again, when we go to the next set of 2, this will calculated by this formula and this will get calculated by this formula. That is how it exactly works, okay. The reason is very simple why we are using in this way, because we should not be getting a similar kind of encoded values. If we get a similar kind of encoded values, then we will miss the order of the elements, right? We'll miss the order of the elements. This is really important to specifically understand. Let's say you say that, hey Krish, why to use this cosine? Instead, just try to use sine, okay? The amazing thing about sine will be that all the values will be ranging between -1 to +1, okay? But if I just use sine, there may be that for same 2 different values, I may get the same sine value, right? For this also, I may get the same sine value. For this also, I may get the same sine value. So that is the reason we may miss the order of the elements or of the tokens, and we don't want this to happen. So what we have done is that we have combined this with another cosine equation, okay? Now what will happen for every vectors? First, if this is computed by sine, the next vector will be computed by cosine. So let's continue this particular findings with respect to the positional encoding. So now my third one that I'm actually going to compute over here will be sine of 0, 2. See, I will be into 0, 1, 2 at this position. I have to use sine. Here I have to use cosine, right? So this will basically become sine of 0. And then we are going to use 10,000, 2 by 4, okay? But again, here I'm actually going to get sine of 0. Then again, this will be 0. And finally, we will go ahead and compute the positional encoding of 0, 3. Again, we are going to use cosine. Again, this entire value will become 0 and this will be 1. So with respect to our first word, right, what is the positional encoding that we are getting? It is nothing but 0, 1, 0, 1, right? Now, similarly, if we go with respect to our position 1, right, position 1 is with respect to our second word, right? So if we go ahead and calculate it, so let me just go ahead and write for position 1. So for position is equal to 1. Now I'm just going to use the same formula. First of all, I'll write position encoding for 1, 0. 1, 0 basically means my second vector. So this is for this, and this one will be my second vector, which will be represented by another 4 dimension. The positional encoding will be shown by, and this is for this particular word. The positional encoding is for this word, okay? And again, I have that same operation that I have to do. And when I say position 1, that basically means we are going for the first word, right? And finally, after that, we'll go for the second word. So positional 1, then again, we go ahead and compute it. It will be sine. Again, it will be 1 divided by 10,000, okay? 0 divided by 4. right? Why 0 divided by 4? Because I is 0. So again, I'm going to get sine of 1. Sine of 1 is nothing but it is approximate. If you go ahead and calculate it, it is 0.8415. So similarly, we will go ahead and calculate the post encoding of the position 1. So over here, we will go ahead and compute now the post encoding of positional 1 with the I value is equal to 1. So again, here, what formula we are going to use? We are just going to write cos, and let's see the formula. So I will also make sure that I will try to specify this formula over here so that you will be able to refer this. Okay, so here I'm just going to copy it. I'm going to paste it over here. The next formula, again, I will select this and I'll paste it over here. Okay. So once I'm calculating this, okay, please try to understand over here. So I'll select this right now. Okay, so I'll keep it over here, and similarly this I will keep it here for my reference. Okay, so here when I am calculating with position 1 and I is equal to 1, so if I really want to use the cosine value, so this I that you will be specifically getting, right? So here I will write position value 1, okay, 1 divided by 10,000, okay, to the power of 2 of I, right? So 2 of I is nothing but over here I'll just go ahead and write 2 multiplied by 1 divided by 4, and this whatever approximate value we'll be getting, we'll get it 5403. Similarly, you can go ahead and calculate the post encoding for 1, 2. Again, we have to use the sine formula, and with respect to the sine formula, just go ahead and write over here 1 by 10,000, 2 by 4. This will be approximately again equal to 0.01. And again, once we go ahead and compute it for 1, 3, again I have to use my cos value. Just try to do the computation. Okay, I'll leave it up to you. So here I will be getting my value as 0.995. Okay, so in short, here what we have actually done is that the word that we have specifically taken, right? Cat. First of all, I will just go ahead and write with respect to the word. So for the word, so here you can see for the word, which was given by the vectors, right? 2, 3, 4. The vectors for that we have actually used is 0.1, 0.2, 0.3, 0.4. So here, if I go ahead and write, this is 0.1, 0.2, 0.3, 0.4. For this, we have converted this into some other encoding. And here, the positional encoding is nothing but this value, that is 0, 1, 0, 1. Okay, so here we have specifically got as 0, 1 and 0, 1. So this is the positional encoding that we are able to find out for this particular vector, right? For this vector. Similarly, for the word cat, initially we had this vector, and after performing the positional encoding, you'll be able to see it was 0.5, 0.6, 0.7, 0.8, right? So here I will go ahead and write 0.5, 0.6, 0.7, 0.8. This, we were able to get an encoding of the values that we got over here, 2, 3, 4, and the values were nothing but these all values, 0.8415, 0.84, then you got 0.54, and then 0.01 and 0.995 or 995. Okay. Now this is how you have actually got the positional encoding, and through this way, what you are actually doing is that we have to probably sum up these values, right? So finally, you'll be able to see whatever self-attention I will be giving right over here, whatever vectors I will be giving in this self-attention layer. Okay, it will be the combination of your vectors that we are specifically getting with the positional encoding. That is nothing but 0.5, let's say, sorry, not 0.5, 0.6, but instead I will write 0.84. Or let me just go ahead and remove this, and let's use an positional encoding. Here it will be 4 dimension again, based on the problem statement that we have done. In the research paper, it is taken as 512 dimension. Okay, you can go ahead and check out the research paper. So 0.84, 0.54, 0.01, 0.9999. Okay, and this we have to sum it up with our vectors that we have actually calculated, right? So for the cat word, this will be the word that will be going on 0.5 plus 0.6 plus 0.7 plus 0.8. Similarly, for the other vector that we have, right, again, the ordering can be placed over here also, it can be placed over here, but we are handling it with the help of, because all the words will be going parallelly, right? Now this positional encoding is making sure that whatever values we are putting, it knows the order now, right? So for this, let's say the value was 0.1, 0.2, 0.3, 0.4. So for this, you are actually getting nothing but 0, 1, 0, 1. And this is also going to get summed up. After the summing up is going to happen, then this entire value is going to go to the self attention. And finally, we are going to give entirely this to our feed forward neural network. And here we are going to get our Z1. Here we are going to get our Z2, considering the multi-head attention is applied. But these values that we have actually got, sorry, here I just need to reverse this. Okay. So this needs to go down and this needs to come up. Okay. Because this is the positional encoding. Okay. So this were my word vectors. So if you probably go ahead and see with respect to the cat, this is the vector that is getting created. This is with respect to this is my positional encoding to making sure that what word is gone and which order it is gone. But in this case, the has to come over here, cat has to go over there, right? And similarly over here, this is my positional encoding. Please don't get confused. I've just changed the order here itself, okay, purposely. But it won't matter a lot because anyhow, I'm giving the positional encoding information so that to make sure that which word is coming after what, right? And then we finally give it to the self attention. And here, if multi-head attention is basically there, you know what is exactly happening in the self attention, then all this multi attention will be given to the neural network. Okay. That is feed forward neural network. And finally, we get this, that is Z1 and Z2, which will be our contextual vector. So this was the overall idea about positional encoding. But in short, if you really want to know about positional encoding, it's more about, it's more about making sure that the order of the words is taken, the representation order of words or sequence is given to the self-attention layer in some way, right? We need to make them know, okay, this is the first word, this is the second word in the sentence. Obviously, this problem will not happen in RNN because RNN, we give one word at a time with respect to timestamps, right? So this was one of the most efficient technique that we used. One more technique is something called as learned positioned encoding. Now, in the case of learned position encoding, what we do is that in this case, positional encodings are learned during training. Okay. During training. Now, when we say during training it is learned, that basically means we need to create a positional encoding matrix over here, and it needs to get updated through backpropagation. Again, I don't want to discuss more about this because I think in the research paper also it is mentioned about sinusoidal position encoding, right? And this is nothing but it is a combination of sine and cos. We keep on creating this so as that no two values with respect to our positions, no two values should get the same value over here with respect to the encoding. That is the reason we specifically use this. Hello guys, so we are going to continue the discussion with respect to transformers. Already till now we have discussed about many things, right? We have covered something called as self-attention. Then after covering self-attention layer and how it exactly works, we have also understood about multi-head attention. Then after covering multi-head attention, we saw the problem with respect to the sequence of word. And for this, we also understood about what is the importance of positional encoding, right? And we have actually seen a lot of examples. I have personally done all the calculations, how with the help of self-attention layer, how we can convert that fixed vectors that we specifically had from the inputs to contextual vectors, right? So all those things we have specifically covered. So in this video, we are going to go ahead and understand about something called as layer normalization. Now, near normalization is one of the component. Now, if you see the architecture of the transformers, and this architecture is from the research paper, here you'll be able to see that initially I have my inputs. We convert this into some input embeddings. Then we add it with the positional encoding. And after this, we go ahead and create our multi-head attention. So here we specifically pass through our self-attention layer, right? Now, when we are creating this multi-head attention, now you can see the next step, what exactly after this it is, right? It is basically called as add and normalize, okay? Add and normalize. And this is what we are going to talk about, right? When we say add and normalize, the normalization technique that is specifically applied is called as layer normalization. So we are going to understand the mathematical intuition. Along with this, there is also one more topic that we really need to understand, which is called as residuals. Now here you can see that before going to the multi-head attention, whatever vectors that I get after adding the positional encoding to the input embedding, that is also passed to this add and normalize. So this are called as residuals, okay? Residuals. And this provides some additional signals, okay? Additional signals to the add and to the layer normalization, right? Layer normalization. It's just like this line is basically providing the information of this input embedding plus positional encoding vectors to the additional and normalization layer, right? So in short, that is the reason we basically say here we are saying add and normalize. So we are going to probably add this previous encodings that is probably coming from the input embedding and positional encoding, and then we are basically going to normalize, right? So that is basically the residuals that is getting added. So this is the information, whatever pre-hand we are able to get, that we are passing it to the next stage. Okay, and that is what residuals is all about. But again, don't worry, we will try to understand it, what exactly is normalized and how this addition and normalization takes place. Okay, now before we go ahead, let's understand where this addition and normalization will get added. Okay, so here again, I've taken this particular diagram from the blog, right? So here you initially have your input embeddings, okay, layer by layer it will be there. This is for my word 1, word 2, right? Then for each of these words, based on the number of attentions, I will be initializing different weights, right? Then we probably go ahead and find our query, key and value vectors for each and every attention. And finally, we get all the attention itself, right? Z0, Z1 and Z7. Now see one thing over here. Where does this, see, because this is the multi-head attention, right? And this multi-head attention, before we pass it to the feed forward neural network, right? So here we will go ahead and apply our next step, that is nothing but add and normalize. So let me write it in another color, add and normalize. Okay, and this is where your layer normalization basically happens. Layer normalization basically happens. Now, what exactly is this layer normalization? We'll discuss more about it. But with respect to the kind of working that you'll be able to see, that over here add and normalize is specifically happening. Okay. And here you can see once we also provide this, before we go ahead, we also need to add our positional encoding. Okay. And this positional encoding will be like with the same shape, right? So let's say if this is my positional encoding. So here 1, 2, 3, 4. So this will be my positional encoding that will get added and it will be sent over here. Along with this, what happens is that this positional encoding information is also sent over here and it is added before the normalization takes place. Okay. And the reason over here why we do this, because we are providing the signals, this entire information to this layer. Okay. Some more additional signals. So that is what residuals is all about. Now let's go ahead and understand about the layer normalization. So first of all, we will just get to know an idea about what exactly is normalization. And specifically with respect to deep learning, we use normalization in two different ways. One is batch normalization. One is batch normalization, and the other one is something called as layer normalization. Batch normalization and layer normalization. Now let's discuss about this batch and layer normalization. So for this, I will take an example. Let's say I have a neural network with two inputs. Okay. And let's say here in my hidden layer, I have two hidden neurons. And then finally I have one, right? So whenever this input is basically connected to the hidden layer, right, in this way, and then finally I'm able to get my output over here. So this is my output. Now what exactly is normalization? See guys, let's say over here I am having two features. Let's say my feature is like house size, right? This is my first feature. Let's say I'll go ahead and write area of the house. Okay. House size and area. I'll say number of rooms in my second feature. Number of rooms. And I need to probably predict the price of the house. Okay. So this is my F1 feature. This is my F2 feature. And this is what F1 feature goes over here. F2 goes over here. Now, before we usually send our F1 and F2 input to this particular ANN, that is artificial neural network, or I can also say it as feed forward neural network, right? Here I will be having some information, and one by one, I will probably send this information for training the neural network. Now, what usually happens is that the first step, and you know that, right? I will be having multiple values over here. Let's say I'll just go ahead and write what is the house size. Let's say it is 1200 square feet. Okay. Number of rooms are 2, and let's say the price is 45 lakhs. Okay. And I will go ahead and write, hey, my house size is, another house data that we have is 1500 square feet. The number of rooms are 3. And this is 70 lakhs. Okay. And similarly here you have 2000 square feet. You have 3.5 BHK rooms. And here let's say the price is 80 lakhs. So all this information you specifically have. Now the first thing that we basically do before we provide all these inputs F1 and F2 for the training, right? What do? We do something called as normalization. One of the most common normalization we do, right? That is nothing but standard scaling. Now what does standard scaling basically mean? With the help of standard scaling, right? What we do is that we take each of this features, right? Each of these features, even the output feature if we want, and we apply a general standard scaling formula, and that we basically say it as Z-score. Now in Z-score, what happens is that the formula is very simple. We take every input, we subtract it with mean, and we divide by standard deviation. Now once we do this, if we are considering any feature, let's say if I'm considering house size, and if I apply this formula, all these values, you will be able to see that we will be getting in such a way where my mean will be 0 and my standard deviation will be equal to 1. Okay. So what is basically happening? Let's say if F1 is one of my distribution, after applying the standard scaling, this will get converted into F1 dash, and inside this F1 dash, here you will be able to see my mean will be 0 and my standard deviation will be 1. Okay. Now, one thing that you really need to understand, right? Whenever we are applying this formula, this basically gets applied to this entire column. Okay. To entire column. So first of all, what we need to do in order to apply this formula, we need to calculate the mean for this. We need to calculate the standard deviation for this. And then for every number, we will go ahead and apply standard scaling. This is what happens when we try to provide our input over here, right? When we provide our input over here. Now this scaling is fine. Okay. And usually we do this. And what usually happens because of this, I will tell you. There's some very good advantages of using this. And similarly in deep learning, if I talk about deep learning, right? In deep learning, let's say my input is in the form of images. So there also we do some kind of scaling, and that scaling that we specifically do for the data is something called as min-max scaler. Now in the case of min-max scaler, you know that all your images, right? Let's say I have some color images of this, of some 4x4 matrix. And you know, all the values will be between 0 to 255. So what we do after applying this min-max scaler, we convert all these dimensions between 0 to 1, right? 0 to 1, 0 to 1. All these pixels that we have, right? If it is 4 cross 4 pixels, so we try to convert this into, 0 to 1. So this usually we do for the input data, whatever input data we specifically have. And what are the usual advantages for doing this scaling techniques, which we also say it as normalization? First, let me just go ahead and write some of the advantages. The first advantage that I would like to write is about improved training stability. Okay. Now, what does this improved training stability basically means, right? See, before we are passing it to our ANN, right, all the information, we know that my data may be following a different kind of distribution. It can be this distribution, it can be this distribution, it can be probably this kind of distribution, different distribution it may follow, right? And when we actually convert this distribution into a distribution where all my information is centered near to 0, right? Because here what is happening? Here we are able to convert into data where our mean will be 0 and it will be standard deviation equal to 1, right? So, and all the values that you will be seeing, let's say initially when I probably check the distribution, let's say that I'm checking the distribution between my F1 and F2 feature. Now, you know, my distribution is coming over here. Let's say it is coming over here. Now, what we are doing after applying scaling, it is very simple. We are taking this, and this is my F1 and F2. Now, here my magnitude was, I'm trying to bring all the magnitude over here, right? So here, what is the mean property over here? Your mean will be equal to 0 and your standard deviation will be equal to 1. This entire distribution will have this kind of distribution itself. Now, because of this, what will happen is that when we are doing the back propagation, okay, we will definitely not face any kind of problems related to vanishing and exploding gradient problem. This is one of the properties that we usually get after doing the scaling. And right now, all the scaling has been done in the center, right? If we had this huge values, there may be scenario that whenever we are doing some kind of multiplication with respect to the weights and all, these values will be quite huge. Okay. And because of this, what will happen is that the second important thing that may happen is that we will be able to get faster convergence. Because obviously these values are very slow, less, right? So if you remember the gradient descent, with respect to our weights, we try to find out our loss, right? Now, since our values are already centered completely, right? This is 0 centered. All the data over here is like 0 centered, right? You'll be able to see that initially, if I compare with respect to our weights and loss, our loss when we are doing this, when we are probably doing the scaling, initially it will be very, very small. If we don't do this, there may be scenario that there may be a huge loss over here. And then our main aim is basically to come to the global minima, right? It can be from here, it can be from here, it can be from here, it can be from different position, right? So because of this, we are able to do the faster convergence. And the best thing will be that when we apply back propagation, there will be a stable updates. Okay, perfect. Then one more important information that I really want to talk about, right? And that point I will discuss later on. But first of all, this is one of the way how we do the scaling. But again, if I take this particular neural network, okay, let's say this is my neural network, this is my input layer, this is my hidden layer, and this is my output layer. Now you know that this is connected to this, this is connected to this, this is connected to this, and I have this, right? Now here you will be able to see that if I am doing all the normalization with respect to F1 and F2. Now you know over here we have W1, we have W2, we have W3, we have W4, right? Now in the hidden layer, if I just consider as an example, let's take this as an example. Let's say I will just go ahead and take some house size, right? Area, rooms, how many number of rooms are there? And this will basically be my price, okay? So let's consider this three features I have, okay? The first feature with respect to the house size is, let's say 1200 square feet. Now, after I probably do the scaling, let's say I have some values like 1, or I'll just put some smaller value, okay? Let's say 0.45, okay? Rooms, I will just convert this into 0.55, and price, I will keep it like that only, 45 lakhs, okay? Then again, this can be 0.60, this can be 0.20, this can be some other value. Similarly, I'm just putting some values over here, okay, after doing the scaling. And this is my F1, this is my F2, I'm sending this value, okay? Now, you know that when I'm sending F1 and F2, right? So first feature I have given over here as 0.45, and this is my 0.55, right? Now, what is basically happening over here? The first, what I will do for this particular node, we will go ahead and see that the first Z1 that we will go ahead and compute. And here, you know that a bias is added, B1, and here bias 2 will be added. And top of that, activation function will be applied. So inside this Z1, we will try to apply an activation function. Let's say I'm going to apply a sigmoid activation function. So what is my first feature 1 value? It is 0.45 multiplied by, okay, W1. Okay, so this basically becomes my W1. Then 0.55 multiplied by, what is this? W3, right? Once we do this, then we are adding a bias, right? We add a bias, that is B1, right? Now, once we do this entire calculation, we pass it to the sigmoid activation function. We get some value. We will get some value over here. You can go ahead and calculate the value if you want, okay? You can initialize any weights and all, okay? Now, similarly, I will go ahead and do it for Z2, right? Z2 is the output of this. So Z1 is here and Z2 is over here, right? So in the case of Z2, again, I will go ahead and apply sigmoid activation function. With respect to that, whatever value I'll get, here I'll add a bias, and this will be my another value, okay? So here I'm getting my value 1. Here I'm getting my value 2, okay? If I probably consider this in the form of matrix, it is very simple. How many weights are basically getting created? 2 cross 2. So here the output that I'm actually going to get is 2 cross 2, right? So here you can see 2, 2, right? So 2 cross 2 will be basically my output, okay? 2 inputs I have. So this is 1 cross 2. Then with respect to this, you'll be able to see that I'm passing it through all the weights over here. So it will become a 2 cross 2 matrix, okay? So this is fine. Let's discuss more about this, okay? Now let's observe this. So this is my value 1. This is my value 1. This is my value 2. Now when I have this value 1 and value 2, initially when I gave this F1 and F2, obviously we have done the normalization. But after doing all this kind of multiplication, don't you think this value 1 and value 2 value will change when compared to the distribution of F1 and F2, right? Whatever multiplications that we are doing over here, does this distribution may change? Does this distribution may change? So here, let me just go ahead and write it over. Here Z1 is nothing but some value. Z2 is some value, okay? Similarly, for all the other inputs, I'll be getting some value. So whatever inputs, whatever calculation that we are getting over here, don't you think this may have a different distribution when compared to this feature 1 and feature 2, right? It may have a different distribution. And that is what is the problem, right? Because the distribution is getting changed, right? It may have any kind of distribution over here. This and this distribution will definitely get changed, right? And for most of the problem statement, we feel that, okay, this distribution should not be getting changed when compared to your input features distribution, right? And it is always good to have a normal distribution at each and every place. But here what is happening, because of so many different types of operations that you have done, the entire distribution is getting changed over here. Now, because of this, what we have to do is that in order to make sure that the distribution does not change very much in a way that it impacts the entire training of the artificial neural network or any neural network, what we do is that we further go ahead and perform normalization on top of Z1 and Z2. So here we go ahead and perform normalization in every output Z1 and Z2. And this normalization is basically called as batch normalization. So in the case of batch normalization, we take this entire values of Z1, we normalize it. How to normalize it? I will talk more about it. I will just show you the formula over here. Okay. And this Z2, so for this Z1, if I really want to normalize it, what I have to do? I have to go ahead and compute the mu, the standard deviation, let's say mu1 and standard deviation for this. And for every number, we will go ahead and apply the formula. Okay. And similarly for Z2, if I really want to normalize it, again, I will go ahead and compute the mu2 and sigma 2, standard deviation of 2 for that particular Z2. And for every number, I will go ahead and apply my Z score. Right. And that is how the entire normalization probably happens. Right. By doing the normalization, again, our distribution will start matching this particular distribution, because again, what we are doing when we do some kind of normalization over here with the help of same Z-score value, you'll be able to see that my mean will again be coming to 0 and my standard deviation will be equal to 1 or near to 1. And when we are doing that, that distribution will start matching with your features 1 and feature 2. Okay. So this is batch normalization. Now, what is the difference between batch normalization and layer normalization? I will talk about it. Okay. So here, let's say I will also go ahead and talk about batch normalization versus layer normalization, because if I probably consider my neural network, okay, because if I consider transformer, so in transformer specifically we apply layer normalization. Okay, so let's say over here I have my feature 1, my feature 2, okay, and this was my Z1 output, this was my Z2 output, right? I had some values over here, right? So I had some values over here. So batch normalization says, hey, go ahead and normalize each and every value like this, right? This was batch normalization. Layer normalization says, hey, instead of taking the complete Z1, what you do is that you take layer by layer. You take layer by layer and then you normalize them. So you normalize in this way. For this, you go ahead and compute your mu1, sigma 1 and apply your Z score with respect to x of I minus mu1 divided by sigma 1. X of 1 will be this, x2 will be this. Similarly, for this, you go ahead and calculate your mu2, sigma 2. Then you go ahead and calculate your Z score. That is nothing but x of I mu2 by sigma 2. And similarly, for this, you go ahead and compute mu3 and sigma 3. And for this, you go ahead and apply your Z score, x of I mu3 divided by sigma 3. Okay. And this way you specifically normalize in layer normalization. This is the basic difference between batch and layer normalization. So guys, I hope you got a basic idea with respect to batch normalization versus layer normalization. Now let me talk about two important learnable parameters that is called as gamma and beta. Okay. These learnable parameters are also used while we are training our models. Okay. Now what are these learnable parameters? Why it is specifically used? We will discuss about it. But before that, what is the use of layer normalization? That we'll try to see. Let's say over here, I have Z1, I have Z2, okay? And this Z1 and Z2 is what? It is basically the output from here, right? So here we are basically talking about, right? And like that, we can have any number of hidden layer. For every hidden layer also, it is a good idea that we actually perform batch normalization, okay? Now let's say with respect to Z1 and Z2, I have different values. And with respect to this, let's say I'm also having some 0 values, okay? Let's say over here also I'm having 0 values. Okay. Now for this values that I have, what is the use of doing layer normalization? See, in batch normalization, what we do, we take this entire Z1 output, Z2 output. When I say Z1 output, see, I'm basically considering the output of both of them. Okay. Both of them in short, in the form of this particular matrix. So Z1 at one side and Z2 as one side, right? It is in the form of matrix itself. Okay. Now understand one thing over here. Okay. Very simple. If I have many number of zeros over here, if these are zeros, basically the output is not coming up anything, right? When we have this kind of normals, when we have this kind of numbers, so here we are definitely performing batch normalization, right? We are taking this entire batch and we are normalizing it. Okay. Now, once we are doing this, you know that most of the values are zero, but for all these zeros values also, we are still normalizing it, right? And we are normalizing how? By calculating your mean value for this. Okay. And then along with this, you are calculating your standard deviation, and then you are applying Z-score for each and every number. Now, when you apply the Z-score for each and every number, these values are also going to change, right? Some other values will definitely come over here. Similarly, over here, you have this zeros. Now, what is basically happening? This zeros is impacting the entire distribution. So this entire distribution will get impacted because of this normalization, right? So usually in ANN and all, we definitely apply batch normalization, but in transformers that we have seen, we specifically go with layer normalization, because in transformer, we have this NLP kind of use cases where every word is specifically important considering the context of all the other words, right? So what we do in layer normalization, we go ahead and take each and every combination. We basically take each and every layers combination, and then we go ahead and normalize it. Now let's say if I have 0, 0, even though we go ahead and normalize this, I know I'm going to get the mean is equal to 0 for this. If I go ahead and calculate, standard deviation is also 0. So no much impact. No values is going to change. Similarly, over here also no values is going to change. Similarly, if I have 0 over here, no values is going to change, right? This is the most important thing and the basic difference between layer and batch normalization. Now, one more question that comes in mind. Chris, is it compulsory that we always have to do this normalization? What if the final output of Z1 and Z2 that we are getting, and this distribution may be important for predicting the output, and that point of time, what if I do not want to do the normalization? Okay, because I'm considering, hey, for my problem statement, whatever distribution I'm getting in Z1 and Z2, that is perfect for my execution. Let's say for my solving my problem statement. So if I do not want to normalize this, so for that we will be using two learnable parameters, that is gamma and beta. And this learnable parameter will be specifically learned when we are training our entire neural network, right? So now let me just go ahead and write again. So Z1, if you are calculating, it will be some function. Let's say I'm going to go ahead and apply my sigmoid over here, right? And this will be W transpose X, whatever transpose we are specifically doing with B1, right? Or whatever B1 weights we are specifically getting. After this step, what happens is that we assign learnable parameters, okay? And this learnable parameters, I'll just write it as Y. Y will be my output. And here I will be using gamma, okay? Gamma. And then I will go ahead and use this X, Z1, okay? Minus mu1. Z1 basically means all the numbers over here. We are going to subtract with minus mu1, which we are going to calculate it. And then along with this gamma parameter, we are also going to use one beta parameter. And these are the learnable parameters. Now you can see that, right? Learnable parameters. Let's say if our distribution is not important over here and we don't need to normalize it, right? Then based on this gamma and beta value, we can make sure that we can tell, hey, do not normalize in this scenario, or normalize in this scenario based on the data that I have, right? So that is the reason we use this gamma and beta value. I will be showing you this entire example by solving a simple problem also as we go ahead. But I hope you got an idea with respect to your layer normalization and batch normalization and how this entire layer normalization is probably taking place. And we specifically use this two important parameters, that is gamma and beta. Okay. Now, I hope you have understood till here. Now we can go back over here and we can see why add and normalize is basically coming over here, because after this particular output that I get, okay, it is really important to understand, okay, after this particular output that I am actually getting, once we combine this entire entire output with respect to the sequence length that we are getting, right? This output is going to get added with this plus this, which I will mention it as x dash. So x dash is going to get added with this entire values, right? And then we are going to apply our layer normalization, right? So here we are going to specifically apply our layer normalization. Okay, perfect. So that is what is all about layer normalization. Now, what I will do, I will go ahead and solve a basic problem, okay, just by putting some numbers. And when we use this gamma and beta, these are also called as scale and shift parameters. So this gamma and this beta is also called as scale and shift parameters. Okay. Now let us go ahead and let us take a simple problem. Okay. So I will take a simple problem where I will take an example of cat as a token. Let's say I will denote this cat as token embeddings like 2.0, 4.0, 6.0, 8.0. Let's consider that this is my 4 dimension. And the next parameters that I'm actually going to define is my gamma and beta, because these are the learnable parameters. Initially, this will be initialized. Later on, we'll train them, we learn them. 1.0, 1.0. So let's go ahead and initialize this to 1.0. And beta, I will go ahead and initialize to 0.0, 0.0, 0.0, 0.0. The reason is very simple. I've seen the research paper and they have initialized this. Okay. Now we will go ahead and perform step-by-step calculation, like how specifically it happens with respect to the transformer and how this entire process basically happens. Okay. So we will just go ahead and apply this normalization. We will try to calculate, we'll try to find out the normalized vector. Then we'll do the scale and shift, and then we'll finally get our y value. Okay. So this entire computation that we'll do. Remember one thing over here, I'm not taking W transpose X. Instead, I'm directly taking this particular vectors, and how one vector gets normalized. That is what I am actually planning to show you. How these vectors will get normalized. Okay, normalized. That is what I'm actually going to show you over here. So let's see this in the next video. Hello guys, so we are going to continue the discussion with respect to our transformers. Now in this video, we are going to discuss about the entire encoder architecture. Already we have discussed about self-attention, we have discussed about multi-head attention, we have discussed about positional encoding, and so many different topics we have also discussed. We also discussed about layer normalization and each and everything. But now based on the research paper, we'll just try to discuss how the entire architecture is, because this is just one encoder, right? And this is just one decoder. So right now, first of all, we'll focus on encoder. But initially only I told you, right? Based on the research paper, you will be seeing that there will be 6 encoders like this, right? So there will be not one encoder, but instead of this, there will be 6, like 1 encoder, 2 encoder, 3, 4, 5, 6. Similarly, there are 6 decoders, okay? And with respect to any task like machine translation, you give your input over here, you get your output over here, right? So this is the part that we are specifically going to discuss about, okay? When I say this is just one encoder, that basically means this part can be mentioned in this way, right? If I probably expand this, it is nothing but it is basically this entire encoder part, right? Similarly, you have other encoders also, because after the information is basically coming out of this, it will go to the next encoder, then it will go to the next encoder, then it will go to the next encoder and all, right? So based on the research paper, let me just go ahead and write some very important information. So first of all, the input that you specifically take, right? You convert that into vectors. Then you add a positional encoding on top of that. Then you pass through a self-attention layer, right? So if I probably show you the flow, it looks something like this, right? So I'll show you step by step, like how things basically happen. And then we will just try to understand like how many embedding vectors is specifically used and all, okay? So let's say this is your input sequence. So here is my input sequence. Now from this input sequence, what we specifically do, we go to the next step. In the next step, we are specifically going to convert this into vectors, that is through text embedding techniques. It can be any embedding techniques. Plus we add it with positional encoding. Okay. So once we add this with positional encoding, so this is what your input encoding plus positional encoding is basically going on, right? The input sequence, when it is converted into text embedding, so the number of dimensions that is specifically taken for the text embedding, it is nothing but 512. Okay. That basically means every word is converted into a 512 dimension based on the research paper. Okay. So in the research paper it is mentioned, when they tried to entirely create this, initially they used this 512 vectors for every input sequence, right? So positional encoding will also be same, right? Then after we pass through this, what we get our multi-head attention, right? We get our multi-head attention, and this is where your self-attention works, right? Between this multi-head attention. Now, multi-head attention basically means how many different head attentions you have over here. So if I probably talk about here, you have 8 head attentions like Z2, Z3, Z4, Z5, Z6, Z7, Z8. So this is also based on the research paper. So in research paper, how many attentions head they specifically used? 8. Okay. Then before we go ahead and pass this information from multi-head attention, here what we are specifically doing here, we are first of all adding and then normalizing. So that is the reason we say add and norm, right? The normalization technique that is specifically used is layer normalization. So here what we are doing, before doing this, we need to add this information that is probably coming from this layer. And this is what is called as residuals. Okay, this is basically called as residuals. What is the importance of this? Just imagine before I do the normalization, the output of the multi-head attention is also going, and we are adding the text embedding and positional encoding information. So that basically means we are giving some additional signals, right? So we'll try to understand. I'll write down point by point what is the importance of this. So residuals is basically over here. Then after doing the normalization, we basically send it to the feed forward neural network. Right. So these are all the steps that we are specifically using. In the feed forward neural network, it will be something like this. This will basically be my input. The input will be based on all these dimensions that we are getting. And then we have one hidden layer. In this hidden layer, we have somewhere around 512 hidden nodes. Okay. And then I have my output layer. Okay. So this will basically give you the output based on the information that I have, based on the number of vectors that is probably coming up. Okay. So here, that is what it is basically happening. And this is the input that is coming from this, right? All the input that we are specifically passing, and it will get trained. Once I do all these things, then it is sent to the next encoder, and the next encoder will have all the information with respect to all these vectors that I have, right? But understand, when I say 512, this is with respect to every word. Every word is basically converted into 512 dimension of vectors. Okay. Now this was the basic information, but there are still more information if I go inside attention, right? Self attention. So what are the parameters that is specifically used, right? There are 3 to 4 important parameters over there also. One is your query key value. So what dimension this query key value is, right? Based on the research paper, this is 64, 64, 64. So you'll be able to see inside self-attention when I do the product of query into K, right? Later on, when I normalize and when I have to divide, right? I divide by root of 64, which is nothing but 8. Okay. This is what we are specifically doing, right? We are dividing by 64, and the number of attention of head is basically 8, right? So all this information I've actually mentioned. So these are some of the basic parameters that are specifically used in research paper. Now the question is coming, right? Krish, why 512? Why so many number of encoders? Because see, understand guys, the kind of task that you do is kind of sequence to sequence task. Sequence to sequence tasks are very complex tasks. They are very, very complex tasks, right? If I probably say language translation, it is a very complex, right? You have one language, then we are trying to convert that into other language. There'll be dialects, there'll be so many different things. Now, if I really want to convert this kind of task, just with one encoder, you'll not be able to get a very good accuracy. So we definitely need to use many encoders over here. According to a research paper, they have used 6 encoders and they were able to get good results. Okay. So this is one of the very important thing that you really need to understand. Okay. The second thing that usually comes in your mind, right? And obviously everybody's mind. First of all, why residuals? Okay. Why you need to probably add residuals? Why need to we probably provide some information over here and probably give it to the additional and normalization layer, right? This is the next question that many people will specifically ask, right? And the third question that probably comes, Krish, why to use feed forward neural network, right? So that is also there in your mind, because feed forward neural network, here also you have used one kind of layer. Even though we are doing the back propagation over here, we are updating the weights of WQ, WK and all, right? So we'll try to answer step by step all these things. And again, after thorough research, what are the points, what are the things that have basically been there from the researchers, we'll try to note it down. Okay. And as I've already shown you, self-attention, this is what is the operation that is specifically happening. And this is just a two example, like encoder 1 and encoder 2. You pass your self-attention, you pass this particular information, your input embedding vectors. So this is basically your 512 vectors, right? So this is nothing but 512. This is also 512. Okay. Then positional encoding will also be 512. Then you have to add this. Then what you're doing, you are passing this information to the next layer, that is additional normalization. Then this gets passed to the self-attention. Then after that, a feed forward neural network. Then for every combination of self-attention and feed forward, you are doing normalization. And why normalization specifically used, I've already spoken about it. Right, your input distribution may be different here, and after doing all these operations, your distribution may become different, right? So what we do, we basically do a layer normalization, which we have discussed in our previous video, right? So let's talk about the residual, right? What is residual over here? Any information that I'm passing it to the next layer. Here also I'm passing, here also I'm passing, here also I'm passing. And if you see in decoder also, here also you are passing. We'll discuss about decoder later on, but let's focus over here in the encoder. Okay. So residual connection, what it is also called as skip connections. Okay. That are used in neural networks. Okay. Now, let's understand why residual connection is basically required. Okay. First of all, just imagine over here, guys, I'm passing this information to the next layer. I'm skipping the self-attention. I'm also passing what was the input. So if I'm passing additional information, if I'm normalizing it, don't you think this layer will be having more information about the input, right? Even though we are able to probably do we are able to convert that into a contextual vector by using self-attention, right? But based on the research paper, there are multiple reasons why it is basically used. So first one is addressing the vanishing gradient problem. Now, why do we say vanishing gradient problem? Because see, guys, here we have somewhere around 6 layers, right? 6 layers of encoders and 6 layers of decoder. During this particular case, you'll be able to see that as the number of layer increases, there are chances the gradient of loss function with respect to the weights can be very small. And this phenomenon is basically called as vanishing gradient problem. Okay. Now, how does residual help you in this? Okay. So I will just go ahead and write, how does residuals help you in this, or skip connection help you in this? It is very simple. Okay. Here, residual connection create a short paths. Very important point. Gradients to flow directly through the network. Okay. Because of this, the gradient remains sufficiently large. And this even in deep neural networks. Now see what is happening over here. I'm passing this information from here to here. I'm skipping this entire operation of self-attention, right? And I'm passing some additional information. So when this entire information is basically passed, you'll be able to see that we are creating a short path, because see, in back propagation, what will happen over here? All the weights will get updated. And here you're passing some additional information, right? So because of this, it creates a short path for gradient to flow directly through the network. Gradient remains sufficiently large. Okay. Now, because of this, what will happen? The second very important point that I really want to mention, it improves gradient flow. When I say gradient flow, that basically means my convergence will be faster. My convergence will be faster. Okay. Now, if I don't do this, I may face some vanishing gradient problem. Okay. It may also be exploding gradient problem, because if, let's say, if my weights is initialized in a higher way, right, in a very large values. Okay. So when convergence is faster, then obviously your training will be also smoother, right? Now coming to the third point, this actually enables training of deeper networks. Now here in the encoder, you can see that I'm just not using one encoder. I'm using 6 encoders. So this becomes a very large network, right? So very deep neural network, right? So here, because of this, at every part of this encoder, we are doing this particular step that is called as residuals, right? So this will basically enable training of deep neural networks. Okay. So you can basically say that residual connections allow for the effective training of much deep networks by addressing the gradient flow issues and making it easier for the network to learn identity mappings. This enables the model to be very expressive and capable of learning more complex functions, right? So this was about the residual connection that we have specifically discussed. Okay. Now let's talk about over here why we are using this feed forward neural network. Okay. This also you really need to understand. Why feed forward neural network? What is the importance of feed forward neural network? Because I've just given one example with respect to feed forward neural network. Obviously, if you know about ANN, ANN is nothing but it is a feed forward neural network. So here, why feed forward neural network? Again, based on the research paper, I will try to give you the definition with respect to some advantages. Okay. First of all, see, if you have created anytime an ANN, right? Let's say this is an ANN. And in the ANN, let's say in the output layer, you don't have any activation function. So this basically solves a linear problem, right? Sorry, this solves a linear function problem. But the main aim of feed forward neural network is basically to capture the non-linear function. It is to solve the non-linear function, right? Now, in the non-linear function, how do we solve this and all? Obviously, we have seen, right? In every layer, we apply an activation function, right? And based on that, it is able to capture the non-linear functions, the most complex properties within a specific data set, right? The behavior and all, right? So similarly, feed forward neural network will also do that same thing. Obviously, before the self-attention is able to do good task, but to capture more information for this complex task, we specifically use this feed forward neural network. So what it does over here, I will just add one point that it is going to add non-linearity. Okay. Second information, and probably this is even not mentioned in the research paper, but I was reading an article and there I specifically understood about this. Okay. It is nothing but processing each position independently. Okay. Now let's talk about this, why it is important. Now you know that self-attention mechanism captures the relationship between tokens, right? What does self-attention basically do? It captures the relationship. It captures the relationship between the token. It processes the relationship in such a way that each token can attend to every other token, right? That is how it basically captures the relation. right? And that is the reason you don't require further transformation or feature extraction on the representation obtained from the self-attention. Okay. Now, how does feed-forward neural network help? This feed-forward neural network, based on the tokens, whatever context you are specifically able to get, it processes each token representation independently, right? Before, what it used to do, we are sending all the information with the positional encoding. That is how your self-attention will understand which words are probably coming first, which words are probably coming second, right? But if I talk about the feed-forward neural network, this processes each token representation independently. Now you may be thinking, what is so important about me? This means that for each token representation resulting from the self-attention mechanism, the feed-forward neural network applies the same two-layer neural network. As I said, there will be a two neural network, and this helps, since we are taking each and every token and we are trying to retrieve more specific information out of it. This helps in transforming this representation further and allows the model to learn richer representation. With the self-attention, we are definitely able to understand some of the information based on the contextual information. But by using feed-forward neural network, again, we are taking each and every vector for that specific information or for that contextual embedding. And then we are allowing the model to learn more representation from that particular thing, right? It's just like trying to explore more of this specific vectors that are created by the contextual embeddings, right? So this is why we specifically use feed-forward neural network. And if you know about ANN, which is a kind of feed-forward neural network, you can just understand with the help of forward and backward propagation what all information will be able to explore and get. Okay. Again, the third important point about feed-forward neural network is that already our network is really deep, right? So feed-forward neural network helps your model, helps your neural network to become much more deeper, right? So it basically adds depth to the model. And one important property about depth is that if you're handling all those vanishing gradient problem and all, as there is more depth, more learnings you will be able to get from the data. More learnings you will be able to get from the data. So that basically means the neural network will be able to capture more and more information from that particular data. Okay. Now it's not like that you can probably use just 10 layers of feed-forward neural network, but this is doing one thing because the 2 layers is specifically able to do much more things over there, right? And again, when you say one more very important property with respect to feed-forward neural network, it also increases the model parameters. Okay. And because of it, it will be able to help us to generalize well with the training data and with the test data, which is unseen data. Okay. So this is more about understanding why feed-forward neural network, why this and all. But if I just go with the flow, I have each and every word that is passing to self-attention, add normalization, feed-forward neural network, then again passing through the next encoder. Now again, you may also have a question, Krish, why so many number of encoders, right? Again, as I said, sequence to sequence tasks are more complex. So as we are able to extract more and more information, more better it is, right? Tomorrow, if you're planning to create another kind of LLM models or any other models, you can also change this. You can use 4 encoders if you want and all, right? So after all this information is probably passed, then from here it goes to the decoder. Now in my next video, I'll try to make you understand what is exactly about the decoders. But in this video, I told you about the parameters. So let me revise what all parameters are specifically used. One is for the embedding vectors. Embedding vectors is nothing but 512 dimension. Your QKV is nothing but 64. Your multi-head attentions, how many multi-head attentions you have, it is nothing but 8, right? And then along with this, positional encoding will also be the same thing over here. And all the remaining information I've discussed, right? So yes, this was it for my side. I hope you like this particular video. This was about the encoder architecture. I'll see you all in the next video. Thank you. Take care. So guys, now let's go ahead and let me show you an example with respect to all the steps that we have discussed in layer normalization. Okay. So for this example, as I've already mentioned, we will be taking a single token in sequence, going through a layer normalization process within a transformer layer. Okay. So the initial step, we have initialized some values over here. Okay. Token embeddings. Let's say this is the token for cat. It is represented by these vectors. We have initialized some parameters. Okay. And this, parameters basically, when I probably say, right, this is this gamma is your learned scale parameter, okay, and beta is basically your shift parameter. So that is the reason we say it as scale and shift, right? This combiningly is basically called as scale and shift params. Now let's go ahead with the step-by-step calculation. So for the first vector, first of all, we will go ahead and compute the mean. Because if you remember the z-score formula, it is nothing but z-score is equal to x of I minus mu divided by standard deviation. Okay. So here, if I go ahead and compute the mean, so it will be nothing but 1 by 4. Let us take all the vectors values 2.4, 4.0, 6.0, 8.0. And let's go ahead and compute this by 20.0 divided by 4, which is nothing but 5.0. Okay. Next, let's go ahead and compute the variance. Compute the variance. So variance is nothing but your sigma square. So for that, how do we compute it? It is very simple. Sigma square is equal to 1 by 4. Then we take up each and every numbers, okay, and we subtract it. Let's say the first number is 2.0 minus 5.0, which is my mean, plus 4.0 minus 5.0 whole square, plus 6.0 minus 5.0 whole square, and plus 8.0 minus 5.0 whole square. So this is how you calculate the variance. So overall, you will be able to get your variance as 5. Okay. So now here you can see, obviously your mean and your variance looks 5, 5. Okay. So now in the third step, we are going to normalize all our inputs. Okay. Third step, let's go ahead and normalize the inputs. Now in the case of normalizing input, it is xi hat, which is nothing but x of I minus mean divided by just dividing by its root. What we will be basically doing is that we will also be dividing this by standard deviation, but instead of just writing standard deviation, I will just go ahead and give a new representation, square root of variance plus epsilon value. Okay. Now this epsilon value, we will be using a very small value, let's say 1 e to the power of minus 5. Okay. And this is used to avoid division by 0. Okay. This is basically used to avoid division by 0. So here, if I just go ahead and see and calculate this, it is nothing but root of 5.0 plus 1e minus 5, which is equal to nothing but root of 5.0001, which is nothing but 2.236. Okay. So this is my 2.236 over here. And this is what is my below value that is coming. Now we will go ahead and normalize for each and every values with respect to the numbers. So the first normalized value will be xi bar. Okay, let's say, and I will write 2.0 minus 5.0, which is my mean. And here we are just going to divide by 2.236. This is approximately equal to 1.34. Similarly, x2 bar vector that we have, I will subtract 4.0, 5.0 divided by 2.236, which will be approximately equal to minus 0.45. And similarly, coming to the next vector, that is x3 bar, third vector. Here again, we will go ahead and write 6.0 minus 5.0 divided by 2.236, which will be approximately equal to 0.45. And x4 bar will be nothing but 8.0, 5.0, 2.236, which will be approximately again equal to 1.34. Okay. So these are my outputs and this is my normalized vector. So here I have my normalized vector, but still we need to add something very important. So normalized vector, my x bar will be nothing but minus 1.34, minus 0.45, 0.45, 1.34. Okay. Finally, let's go ahead and apply our fourth thing. Still, we have not applied the beta and gamma parameters, which is like scale and shift. So here we will go ahead and apply scale and shift. Now with respect to scale and shift, I will go ahead and write y of I, gamma of I, x of I plus beta of I, right? You know your gamma. Gamma is nothing but 1.0, 1.0, 1.0. So we are just going to scale and shift, okay? Beta is nothing but 0.0, 0.0, 0.0, 0.0, okay? And again, in order to just do this scaling and shifting, obviously just by seeing this particular values, you are going to get the same x bar or final y output, which is nothing but minus 1.34, minus 0.45, 0.45 and 1.34. So in this scenario, when we initialize this particular value, and this is what I explained, if I say, hey, this distribution is important, I will just, this value will be remaining like this itself, and we will be getting the same value. Let's say if you want to change this distribution, some more values will be separate present over here. And based on that, we can multiply and add that particular values, right? So this was the entire understanding about how a layer normalization work. And this we have specifically applied to a specific vectors. I know on these vectors we apply positional encodings, then along with that we go ahead with self-head attention, multi-head attention and all, and then finally whatever output we are basically getting, we add it, right, at the end of the day from this particular architecture that we are seeing. Now similarly, once we do this normalization, you can see over here we are passing this information into feed forward neural network, but before that, again we are going to pass this entire signal back to the next add and normalization, where I will be adding this output again back to my output of the feed forward neural network, and again we'll be performing normalization. So after doing this entire information will probably go to the decoder, which we'll discuss in the later stages. But I hope you got an idea with respect to the entire working, with respect to add and normalization, multi-head attention, positional encoding, input encoding, almost each and everything has been explained. Now in the upcoming video, we are going to discuss about the encoder architecture, what is remaining, and how the entire other operation is basically performed. That I will be discussing in my next video. Thank you. Hello guys, so we are going to continue the discussion with respect to transformers. Now it's time to probably understand about the entire working of decoders. Already in our previous video, we have seen about encoders. We have understood the in-depth architecture intuition and how exactly encoder works. Now let's go ahead and let's try to understand about decoder. To cover decoder in transformers, here I will be providing you a plan of action, how we are going to specifically cover these topics. So here you can see on the right hand side, you have this entire decoder working. Now inside just one decoder, you have these three important components, okay? Masked, multi-head attention, and feed forward neural network. I hope you know about multi-head attention, how it exactly works in encoder and all. You know that. You also know about feed forward neural network. But one information that you'll be able to see from the encoders, right? And in the research paper, we know that there are 6 encoders like this. So the output of the encoder is basically passed to the decoder multi-head attention. Okay. So one line you will be able to see it over here. So we will discuss more about this, what exactly it is. Okay. So first of all, let's go ahead and see the definition. So here it shows the transformer decoder is responsible for generating the output sequence one token at a time using the encoder output and the previously generated tokens. So from here also we will be generating some tokens. Okay. When I talk about decoder, there are 3 main components and we will be discussing them step by step. The first main component is masked multi-head self-attention. So we will try to understand about this. How does masked multi-head self-attention works and why do we use this over here? Okay. So this is the first important component. The second important component is multi-head attention. I hope everybody knows what exactly is multi-head attention from the encoder, but we also say this as encoder decoder attention. Encoder decoder attention. So we will also try to understand about this. Coming to the third one, which is basically called as feed forward neural network. So these are the most important components that you need to know about if you really need to understand about decoders. Just to give you an idea what exactly how does encoder and decoder work over here. So let's say if I am giving some information to my encoder. So if this is my encoder and you know what is exactly there inside your encoder. So if I'm giving this inputs, let's say I want to translate this entire information, right, into some other language. So what will happen whenever I give some kind of input, this input from this output from the encoders will probably go to the decoder, and it should be able to give your output one by one. So this will be my x1 y1 word. This can be your y2 word. This can be your y3 word. This is the basic difference between encoder and decoder. Here x1, x2, x3, whichever is the words that I'm actually passing in the form of embedding layer, in the form of embedding vectors. These are all passed all at once. Okay, all at once. But when we see with respect to generation, you'll be able to see that my output will be generated based on timestamp. So one word at a time. At t is equal to 1, this will get generated. T is equal to 2, this will get generated. T is equal to 3, this will get generated. Right? So that is the basic difference between encoder and decoder. And how this is getting generated, we will talk about this. So we will try to understand decoder based on two mechanisms. One is training mechanism and one is through the inference mechanism. Okay, inference mechanism. Like during training, how this entire decoder is basically trained, and during inferencing, how I will be able, if I give any input to my encoder, how it is basically translating directly to some other words. Because while training, we will also be giving our real output over here, right? So this will, let's say this will be this is y1 hat, y2 hat, y3 hat. No, I will give y1 over here, y2 over here, and y3 over here. And we will do some kind of masking also, or padding and masking. That is what we are going to discuss about. Okay. So, so this is what we are specifically going to discuss about. In the next video, we are going to probably start with something called as masking. The first important thing, masking multi-head attention. So let me just go ahead and write down the topics, what all things we will be discussing over here. So here, the first component that we are going to discuss is something called as masked multi-head self-attention. Okay. So we are going to discuss about this topic, which is the first component in decoder. Okay. And remember over here, we'll also go ahead and divide this. Let's say the first topic will be input embedding. Okay. And then we will again have this positional embedding. Positional embedding. Second step, we will specifically do the linear projection. Now, I hope you know why linear projection is used for calculating your QKV. Okay. Third, we will be doing something called as scaled dot product attention. This also, you know why we need to do it. Okay. Then over here, we will do mask application. And this is what is the additional step in masked multi-head self-attention when compared to the self-attention. Fifth step, we will go ahead and create this multi-head attention mechanism. Then coming to the sixth step, it is nothing but concatenation and final linear projection. And coming to the seventh important step is nothing but residual connection and layer normalization. So if you probably see a self-attention model, and if you see a masked multi-head self-attention, if I take multi-head self-attention, see in your encoder also you had multi-head attention, right? Multi-head self-attention. So what is the difference between multi-head self-attention and masked multi-head self-attention? That is, there is one more step which is called as mask application that is getting added. We will try to understand the importance of this. Okay. So in our next video, let's go ahead and explore this masked multi-head self-attention step by step by taking an example and seeing that what is the use of this masked multi-head self-attention. Okay. And here you'll be able to understand the basic difference between this one, right? Because see, over here also you have multi-head attention. Here also you have multi-head attention. But what is the use of this masked multi-head attention, right? And we will try to understand with respect to training mechanism first of all, okay? And then I will also be showing that during inferencing with respect to a new data, how this masking will separately happen. So yes, this was it from my side. I will see you all in the next video where we'll discuss about all these points. Hello guys, so we are going to continue the discussion with respect to transformers, and in this video we are going to discuss about decoders. Already the plan of action that is probably given in the previous video, we are going to discuss about these three main topics, that is masked multi-head self-attention, multi-head attention, which is also called as encoder decoder attention. Why do we say it as encoder decoder attention? We'll try to understand. Then we'll also be understanding about the feed forward neural network. But now if you see from the architecture, here you have your encoder, here you have your decoder. The differences between encoder and decoder is that instead of just having multi-head attention, here you have masked multi-head attention. So in this video, we'll try to understand the importance of this masked multi-head attention. Okay. And we'll also be seeing that how this entire transformers will also get trained during the training time. Okay. So let's go ahead. And as said, in the masked multi-head attention, if you really want to understand, we will be going completely from the basics, okay? Like how we understood with respect to the encoders, okay? So here you can see that I have a data set. So this is my data set. Now inside this data set, let's say I have a task which I really need to convert my English text into Hindi text, okay? So I want to do a language translation from English to Hindi. So let's say there are 3 words like this in English, and for that you have 2 words with respect to Hindi. Now let's just consider one input data, okay? And with the help of one input data, we'll try to understand. So this diagram that you see, this side is my encoder, okay? Just a single encoder, and this side is my decoder. Now during the training time, what will happen? This parameters, that is x1, x2, x3 will be going from here, right? Then we have our vectors. These vectors will get combined with positional vectors, right? Sorry, positional encodings. Once it is done, then we get this entire input embedding. Here you can see, right? So let me just go and draw this. So once I give my inputs over here, you will be able to see that I will be able to get this specific vectors, and this is added along with positional encoding. So over here, with respect to the inputs, I will be sending x1, x2, x3, and this will be sent parallelly, right, in the encoder. Similarly, once this entire operation probably takes place over here, where it probably calculates your Q, K, V, it probably goes and find out all the attention heads like Z1 to Z8 according to the research paper, then it will do the normalization. Here it will be passing this information over here, which is my residual. Then it will go to the feed forward neural network, and whatever output I'm getting over here, this is ready to go to this multi-head attention. But at the same time, you will be able to see that my outputs over here, Y1 and Y2 will be going, right? And when we say output shifted right, what does this basically mean? This is a very important word. Now let's say guys over here I have 3 words. Here we have only 2 words, right? It is always a good idea that whenever this kind of discrepancy is there, we really need to make sure that we have a fixed set of characters, right? So for this, initially while we are sending the output over here, we are going to make sure that we also make this text padded, right? So let's say now my padding will become like Y1, Y2, and over here I will be using a 0 padding, okay? So let's say that I have used a 0 padding. Why did I use it? Because I wanted to make all the sentences of the same size. In this example, I've just considered 3 words, like kind of thing. The length is actually 3, but again, it depends on the data set, how long also you can actually make this particular sentence. So now when I say I have basically done the output shifted to right, that basically means I have also added 0 padding over here. Now with respect to this 0 padding, again at the last you'll be having 0. I will be getting this embedding. Again, this will go to my positional encoding. It will create a positional encoding, will do the summation, and now it will send the data to the masked multi-head attention. So if you see from this particular point, right, in decoder also this input embedding and positional embedding will occur, but here you're going to specifically do a kind of padding. Let's say for an example, I'm saying 0 padding. Why this is done? To make your sequences length equal. Perfect. Then here you will be able to see we are going to the masked multi-head attention. Now what happens inside this masked multi-head attention? Let's talk about it. So I'm going to create this specific diagram. This will be masked multi-head attention. Okay, perfect. So here you have masked multi-head attention. Okay. Now with respect to masked multi-head attention, what are the steps that is basically going to happen? That is nothing but it is the combination of all these 3 steps. Okay. Linear projection for QKV, this will get calculated. Then you have the scaled dot product attention, it will get calculated. We know this, right, in encoders also. Then we will be understanding about this very important topic, that is mask application. And finally, we'll go ahead and find out the multi-head attentions. We'll understand why this mask application is required. Okay, step by step, we will go ahead and we'll try to do it. Okay, so first of all, let's get an idea about why do we specifically do this masking work. Okay, so which is basically written masked multi-head attention. Okay, so before that, let me go ahead and take a very simple example. I will show you with respect to all the steps that is basically happening in the decoder. This is also happening parallelly. Okay, first I will be getting the information over here. So till here I hope everybody knows, but we need to understand what is basically happening over here parallelly when we are training it. Okay, and here also all your information will be going all at once, but with respect to the output, I will be getting one by one output as I get it with respect to words by word. Okay, let's say if I want to get y1 hat, y2 hat, so like this I'll be getting the output one by one. Okay, so let's take one basic example, and I'm just going to discuss about this. Okay, I'm not going to discuss about this because this is already done. Okay, so let's take a very good example. Now in the masked multi-head attention, but before that, first of all, what will happen? Let's say that I have a sequence. Let's say my input sequence is something like this. My output sequence is over here in my data set. My input sequence is something like 4, 5, 6. Okay. And let's say my 4, 5, 6, and I'll go ahead and write 7. Okay. This is just my input sequence. I'm numbering it. Okay. Then my output sequence is 1, 2, 3. Okay. So this is my training data that I have in my input and output. Okay, input and output. Now let's do one thing. Okay, let's see what will happen step by step. So first step is nothing but it is called as input embedding. In my decoder, the first step is nothing but input embedding and positional encoding. Now with respect to this positional encoding, what is going to happen? It is very simple, right? So here, let's say I know that my output is specified by this 3 characters, right? 3 characters. I'm going to probably make this into 4. How? I will be making padding over here. Let's say I'm considering the maximum length is 4 over here in all this particular data set. So I will just try to make it as 4. I have done it as 0 padding over here. Now with respect to every characters, okay, let's say that every number is represented by a 4-dimension vector. 4-dimension vector. So here now how your output embedding will look like. See, output embedding basically means this output embedding. shifted to right, right? This output embedding. Okay. So here I will just go ahead and write my output embeddings will be very simple. Let's consider that 1 is represented by another vector. Let's say this is 1, 0.1, 0.2, 0.3, 0.4. Okay. Then I have my next embeddings 0.5, 0.6, 0.7, 0.8. Then I have my next embedding 0.9, 1.0, 1.1, 1.2. Okay. Then let's say that final one is 0, right? So 0 padding basically means it will be just 0 only. So I'm just going to write it down over here. So if I just consider this, my entire vector is represented like this. Okay. My entire vector or my entire sentence is represented like this. So this basically becomes my output embedding. Okay. Perfect. Now you know that my output embedding should specifically be going along with positional encoding. Okay. Over here. So here you can probably see positional encoding is there. Let's consider that positional encoding is 0. All the values are 0. So I will be getting the same output embedding. Okay. Now in the next step, what we do, we go to this masked multi-head attention. Now there are some steps that is involved in masked multi-head attention. So the steps line by line, I will be saying. The first step is nothing but we go ahead and calculate the linear projection. Linear projection, that is nothing but for QKV. This also we do in encoder, and you know the importance of this, right? Then in short, we are just calculating QKV. Okay. So once we do that, then the next step that we have is nothing but scaled dot product, and with the help of this, we calculate the attention, right? Attention scores, right? So that is what we specifically get with respect to the scores. And third step that you will be able to see is something called as mask application. Mask application. Okay. So this is what we are basically going to discuss. And here we are going to discuss about two important mask application. One is look ahead mask. I will write it down. And this is like one more is basically we did the 0 padding, right? So this is nothing but it is the padding mask. So we will discuss about both this specific mask. What is this mask techniques? Okay. And then probably whatever steps is after this, you know that, right? We finally need to get our contextual embedding. So that the same thing we will be continuing and we'll try to understand it. Okay. So now let's me go back over here. So this is my output embedding, right? Now in the step 2, so this is my step 1. And remember this step 1 is we have added the positional encoding. My positional encoding is nothing but everything is zeros. Okay. So 4x4 matrix, everything is zeros, right? So here based on this same matrix, I will be getting over here. Now coming to the step 2. Now in the step 2, what we basically do, we do the linear projection for Q, K and V. Okay. So let's go ahead and create. What we are doing in this, we are creating query Q, key K and value V. These vectors we will try to create. How do you create it? By multiplying with W of Q, W of K and W of K. Let's go ahead and initialize W of Q is equal to W of K is equal to W of V. We will initialize this to identity matrix. So if you are initializing this to identity matrix, so anything that you multiply with identity matrix, so I will just go ahead and calculate Q. This is nothing but output embedding, whatever output embedding, I will just initialize it. See, at the end of the day, we will be learning the specific parameters. This will be multiplied by W of Q, which will be nothing but it will be output embedding only, right? Because this is an identity matrix, right? Similarly, if I go ahead and do the K, this multiplied by W of K, which will be nothing but the same output embedding. Similarly, I have my V output embedding multiplied by W of V, which will be equal to the same thing, right? So this is how we calculate the QKV. Okay. At the end of the day, the QKV is nothing but it will be the same values. So let me just quickly copy this. So this is my final QKV for the first iteration, let's say. So my QKV is nothing but it is equal to the same thing, right? So till here, I hope everybody is clear. So this is how step by step it happens. And probably when I go to that multi-head attention, which includes self-attention and all, this is the first thing that is going to happen, right? I will be able to calculate it. Now the third step over here, we will go ahead and calculate our scaled dot product. Scaled dot product attention calculation. Okay, so we will go ahead and compute this. Okay, now in order to compute the attention scores, it is very much simple. How do we compute the score? I will just write a shortcut formula. Q we multiplied by K transpose, right? And then we divide by square root of D of K, right? In this case, D of K is nothing but 4, right? Dimension of K. That basically means it is nothing but Q dot product with K of T divided by 2, right? We specifically do this, okay? Now let's go ahead and do the further calculation for this scaled dot product attention calculation. And here we will be taking the same data of Q, K and V, okay? So now what we are going to do is that we are going to go ahead and calculate our scores. Now in order to calculate our scores, understand when I say Q multiplied by K of T, right? What exactly it is? It is the same matrix multiplied by the transpose of K, right? So this will, like, say if this is Q, okay, and let's say this is K, right? So first of all, I'm just going to probably multiply this with this point. So it should be something like this. 0.1, 0.2, 0.3, 0.4, right? So this will be my K transpose. So that is the reason what you'll do. 0.1 multiplied by 0.1 plus 0.2 multiplied by 0.2 plus 0.3 multiplied by 0.3 plus 0.4 multiplied by 0.4. Then next one will be 0.5 multiplied by 0.1, 0.6 multiplied by 0.2, 0.7 multiplied by 0.3. Then you have 0.8 multiplied by 0.4. Then again, you will go ahead and calculate the third one. This will get multiplied by this. This will get multiplied by this. Okay. Then for the second time, what you really need to do, you need to take this 0.5 multiplied by this, 0.5 multiplied by 0.1, 0.6 multiplied by 0.2, 0.7 multiplied by 0.3, 0.8 multiplied by 0.4. Then what you'll do, then again, you'll take this entire number and then multiply with the second one, right? So here you'll be able to see, I will be creating my separate key pairs, right? So this will be another key transpose where I'll say 0.5, 0.6, 0.7, 0.8, right? So this will be my another key transpose, then another key transpose will be this, then another key transpose will be this. So finally, when you do the specific calculation, and just to give you an idea how the calculation is given, I have probably written down each and every steps over here, but I've done the calculation over here. My final calculation will be nothing but this is simple, right? See, my Q, K, V is all these numbers. When I say Q transpose of K of T, I have to take, this is my one query, right? This is my another query. This is my another query. This is my another query. And similarly, if I probably consider this as my keys, this is my another key, another key, another key, another key. So with respect to everything, I have to probably do the matrix multiplication or dot operation, right? So finally, you'll be able to see that I have already done the calculation. This will basically be my score. The score will be nothing but 0.3. Again, it will be 4x4 matrix, 0.7, 1.1, 0.0. And then we will further do the calculation. 0.7, 1.9, 3.1, 0.0, right? And then I will be having 1.1, 3.1, 5.1, 8, 0.0. Here also, again, you'll be getting 0.0. I have to get this entire 0 because you'll be able to see that last one is just 0, right? Again, in order to show you how the calculation is specifically happening, so I will just make a matrix over here, let's say. So this is my first matrix. My first matrix will be 0.1 multiplied by 0.1 plus 0.2. It is a dot operation and you should understand this. 0.2 multiplied by 0.2 plus 0.3 multiplied by 0.3 plus 0.4 multiplied by 0.4. Okay. Then coming to the next one, right? Again, what I will do, I will take this 0.1 again, okay, 0.1, and here I will take the same query, right? Same query, and I will multiply with this. So here I will go ahead and write 0.1 multiplied by 0.5, then 0.2 multiplied by 0.6 plus 0.3 multiplied by 0.7 plus 0.4 multiplied by 0.8, right? So this is done. Then what? I will go to my next one. Next one is nothing but, again, if I do the transpose of keys, because I have to, for one token, I have to basically do this multiplication or do this dot operation for all the other tokens, just to understand that how much weightage it is basically adding. Then this will, third one query of key will be 0.9, 1.0, 1.1, 1.2. So my third one will be something like 0.1 multiplied by 0.9. Then I have 0.2 multiplied by 1.0. Then I have 0.3 multiplied by 1.1 plus 0.4 multiplied by 1.2. Similarly, the last one will be nothing but this will become transpose, right? Then it will become 0.1 multiplied by 0. Then you have 0.2 multiplied by 0. Then you have 0.3 multiplied by 0 plus 0.4 multiplied by 0. So this is done, right? Overall, this is just for one query with respect to all the keys, right? The last key will be nothing but 0, 0, 0, 0. Then what we do? We go with the next query. This we will try to multiply with the next thing. Then I will be getting my next matrix. Finally, when I do this summation, I'm going to get these values, right? 0.3. So this entire multiplication, if you do, it is 0.3. If I do entire multiplication and addition, this is 0.7. 1.1, 0.4. Then again, the next one, which will be in my next, which will be my next one like this. This will be my next one. And total, overall, you'll be able to see this is also like 4 cross 4, all the multiplication. And finally, you'll be able to get the attention scores. Okay. So this is my attention score where we have specifically done scaled dot product attention calculation. This is the first step. See inside this, right? After linear projection of QKV, we basically do this, right? Now comes mask application. Now what exactly is mask application? We are going to discuss about. So let's go ahead and discuss about it. So here, I'm just going to go ahead and write masked application. Now, first of all, you need to understand what is the purpose of masked application. Okay. And this is probably the most important topic, and I'll try to explain you this with multiple examples. Okay. Here, first of all, I will just go ahead and write it helps. Mask application helps managing the structure. Okay, the structure of the sequences being processed, okay, and ensures the model behaves correctly during training and inferencing. Okay. Now, what are the main reasons of masking? Okay, so what exactly is masking, you'll get to know about it, but you can just understand that it helps to manage the structure of the sequence being processed and ensures the model behaves correctly. Okay, now let's talk about the reasons. Why do we specifically do masking? The first reason is handling variable length sequences with padding mask. Okay. Now see guys, as you all know, during the output, right, I told you, right, when I'm actually calculating the output embedding, I'm also making sure that I do zero padding so that both the sequence length are almost equal, right? So one of the reason why we specifically do masked application is that because we need to handle variable length sequence with pad masking. What is the purpose behind this? Okay, you'll understand this. What is the purpose? The first purpose is that to handle sequences of different length in batch. Different length in batch. Please just wait for some time. I will explain each and everything what I'm actually saying. To ensure, the second point is to ensure that padding tokens which are added to make sequences of uniform length do not affect the model prediction. Do not affect the model prediction. So guys, now let's talk about the second point. To ensure that padding tokens which are added to make sequences of uniform length do not affect the model prediction. Now, let me just explain you this particular point with an example. Okay. Let's say in my input data, I have a sequence. Okay. The sequence is something like 1, 2, 3. And in my output data, let's say this is my sequence 1. In my output, I have my sequence 2. In my sequence 2, I have something like 4, 5, and I have purposely done the padding over here. Okay. So here 0 is nothing but it is the padding token. Okay. We initially need to do the padding. Okay. Perfect. Now, without masking, see, if I just give this data like this, okay, then in my data, since this 0 padding is there, this will influence, please note this point, this will influence the attention mechanism. Okay, the attention mechanism. Now you may be thinking, Krish, how? Right now you're just thinking, okay, 1, 0 is actually added. But just imagine in a real world problem statement, when we do padding, right? Let's say I want to probably, I get the maximum length of the sentence is 100. Okay, or 100 or 200, right? Let's say. And let's say in one of the output, I just have 2 words, y1, y2. Okay. In one of the output, right, I have just 2 words, y1 and y2. So for this, what we'll do? We'll do the padding. And for this, 98 zeros will get added. When 98 zeros are getting added over here, and when we probably send this 0 padding to our self-attention mechanism, don't you think because of this 0, it will influence the entire attention mechanism? And this will in turn, what will happen? Lead to incorrect or biased predictions. Okay, this is the problem. So that is the reason over here we will do some kind of masking, and this masking will be making sure that this tokens, 0 padding tokens, are ignored. So for this, a kind of masking that we are going to do is something called as padding mask. Okay, so here we are specifically going to say padding mask. This padding mask is basically going to make sure that the tokens are ignored. The tokens are ignored. Okay. So in short, if you really want to understand about the masking over here, masking is done with 2 important types, in 2 different ways. One is something called as padding mask, and the other one is something called as look ahead mask. Okay. And in transformer, we take the combination of both of them, but we'll try to understand what is the importance of them. Okay. So let's take the sequences. I have 1, 2, 3, 4, 5, 0. So this is my output. in my training data set. This is my input in my training data. This will be sent to encoder. This will be sent to decoder, but we are still focusing on this, right? Now for this, since I have a 0, right? There is a padding token called as 0, right? So for this, how do we apply a padding mask? So what we do over here is very simple, okay? First of all, wherever I find a sequence of words, if it is not having any padding, right? So what does padding mask does is that, since we need to consider all the 3 sequences, so padding mask for the sequence 1 will be 1, 1, 1. I'm just taking as an example, okay? So over here, 1, 2, 3, because you don't have any 0 paddings over here, so I will be having the padding mask of 1, 1, 1. What about sequence 2? So sequence 2, padding mask will be 1, 1, 0. Why 1, 1, 0? I'll talk about it, because this sequences are available. Here I just have a 0 padding. So I'm just going to mention at 1, 1, 0. Okay. So this is basically my padding mask for my sequence 2. Okay. But we will just not stop here. Okay. We will not stop here. There will also be another type of masking, which is called as look ahead masking. So let's talk about this look ahead masking. Then again, I'll go back to this padding mask. Okay. So the second type of masking, which we specifically use, is something called as look ahead masking. You'll understand it. Why we are just using 1, 1, 0 for 0 padding token. Why we are creating a padding mask of this 0. Okay. Because this will probably get added and multiplied. I'll show you, okay, how things will happen. So in look ahead masking, this is basically called as, and this is used to maintain auto-regressive property. This is used to maintain auto-regressive property. Okay. See, one thing that you know, right? In decoder, whatever decoder I have, okay. Let's say I'll draw it over here. This is my decoder. Okay. Decoder work is to, let's say if this is my encoder, decoder work is basically to, whenever we give any kind of input to our encoder, this information will pass to the decoder. And finally, I should be getting my input 1 by 1, right? 1, 1, 1, like this, 1 by 1. Okay. So let's say if I say, hey, how are you? Okay. So here you should probably in Hindi will say, kaise ho aap? Kaise ho aap? Something like this. So one word should be coming up from this particular decoder, right? Now, you know that in order to find out the output, okay, let's say my 3 words output is over here. If I want to get this word, or if I want to get if I want to predict this word, I need to have the information of this specific word, right? I need to have some idea about this specific word, right? I don't require this further word information. And that is how decoder will probably work, right? Similarly, if I want to probably get this specific word, I need to have the context of this particular word itself, right? So a very important point that I'm actually going to write over here. Why look ahead masking is specifically used, and why do we say maintaining auto-regressive property? To ensure that each position in the decoder output sequence can only attend to the previous position, but not future position, but no future position. And that is what we want, right? We don't want the future position. We don't want the future information. Instead, from the previous information, I should be able to predict. And that is why we basically use look ahead mask. And why this is necessary? For different sequence to sequence task, like language modeling, or you can also say language translation, right? Here sequence is very much important, okay? And to probably do the prediction, I don't require the information of the future token in my decoder, right? And that is how we predict the current token. Okay, so I hope you have got an idea about look ahead mask. Now let's see some example, and we'll try to find out how masking is basically done. Okay, and then we will again come back to this specific example. But let's see one simple example. Okay, with respect to masking. Okay, so here you will be able to see. I will take an example. Okay, so let's take an example. So example is that let's say I have a sequence like 4, 5, 0. Okay, 0 basically means 0 padding. Now for this, what kind of padding mask I will create? 1, 1, 0. Done, right? Now let's consider that every token is a 3-dimension. Okay, every token is basically 3-dimension. 4 is represented by 3-dimension, 5 is represented by 3-dimension, 0 is represented by 3-dimension. So that is the reason what we can do is that we can also use this mask padding and we can extend it to 3-dimension. So let's go ahead and extend it. Okay, so guys, now our task is basically to convert this 1D to 2D mask, right? And for that we need to extend padding mask to 2D. Okay, now how do we go ahead and extend the padding mask to 2D? Understand over here, whenever we have this 1, that basically means it is a real token. 0 is nothing but it is a 0 padded token. Okay, now let's take this example. 450 I have represented as 110, considering that this is a real token, this is a real token, and this is just a 0 token. Okay, now in order to convert this 1D to 2D mask, you'll be able to see that each row in 2D mask will be a copy of the 1D mask. Okay, now understand one thing, guys. This is really important to just understand. How do we apply 2D masking attention? Okay, so first of all, I have already created my 1D mask. So this is nothing but it is a 1D mask, 1-dimension mask. Now in order to convert 1 dimension to 2 dimension, for each token in the sequence, the mask should indicate which token it can attend to. Okay, now when I say which token it can attend to, over here, when I am probably doing the encoding for this, if I'm converting this into vectors, 4 should probably take the context of this token, right? Similarly, 5 can probably take the context of this token. They should not take the context of this 0, right? I don't want my vector to get changed because of this 0. Instead, I want my vector to get changed with respect to 4 and 5, right? So these 2 tokens I really want, right? So what we are saying is that for each token in the sequence, the mask should indicate which tokens it can attend to. Okay. So based on this, if my padding mask is 1D padding mask is this, we will just go ahead and repeat this. I know 4 is there, right? So for 4, I will write 110. That basically means the attention can be changed with respect to 5, right? Then if I go, and this is for the first token, right? This is for the first token. Similarly, for the second token, I will go ahead and write 110. Why? Because I'm saying that, hey, 5 also needs to probably change their attention based on this token 4, right? So both this context should be there. So that is the reason we have repeated 110, 110. This token is basically for 4. This token is basically for 5. And if I probably consider with respect to this can impact this can basically impact this. Okay. This can be a context. I can also basically write over here, token 1 attends to token 1, 2. Similarly, token 2 attends to 2, 1 or 1, 2, right? So this can probably get impacted. Again, I'm telling you what is the exact meaning, why I'm saying it can attend to. Okay. This is important for you all to understand, right? When we say it can attend to, right? In short, we are basically saying that, hey, this token 4 can attend to token 5 in the context of attention mechanism. We can change the context, okay? And we can change the representation. But the final one, if I probably see with respect to the token 0, I don't want this to impact anything. So my when I convert this 1D mask to 2D mask, this is how it is basically going to look at, right? So this is my token 1, token 2. This both can probably change its own attention. So I'm writing 110. Similarly, I have 110 over here, then 000 over here. Okay. So this is how things work with respect to this. And I hope you got an idea with respect to this particular example. Okay. But we'll not just stop over here. Okay. There are many more things that we really need to probably go ahead and discuss. Okay. And that is nothing but we need to also go ahead and apply one more padding. Okay. And how do we combine both of those padding? We will try to understand that. Okay. But I hope you got an idea over here. So this is my extended padding mask. Okay. Then the next step, what we do is that we will go ahead and create our look ahead mask. Now, how do we calculate this look ahead mask? Look ahead mask is also based on which token can attend. See, this is completely dependent on the decoder output. And here the sequence is very much important. Now, if I really want to create the look ahead mask, I know, right, when I probably get the first token, I will keep it as 1. This will be 0, 0 because the further context I don't require. Similarly, I will go ahead and write 1, 1, 0. The second token, if I'm probably getting it, it should have the context of first, not the future. And if I try to probably predict the third one, this should probably have the context of all the previous, not the further one, right? So since I'm working with 3 cross 3, so this will be my another 3 cross 3 matrix. Okay. And if I really want to specify this in a better way, it should be better that I create a separate arrays for this or matrix for this. So this will be 1, 0, 0. Then I have the next one, which is nothing but 1, 1, 0. And I have nothing but 1, 1, 1. Okay. Since we are using 3 cross 3, this is how it is basically going to look. Now in this kind of masking, you'll be able to see the top, everything will be 0, right? And in this masking, wherever the token is 0, I'll be making sure that I try to convert that into an extended mask where this 0 will be created in the similar way. Okay. Now the next step will be that we combine padding and look ahead mask. Why do we combine? With the help of padding mask, you'll be able to see that we are removing all the zeros, right? And how do we do this? It is very much simple. It is basically with the help of element wise multiplication of 2 mask. Okay. Now in this scenario, if I go ahead and combine my mask, so combine mask is nothing but we will go ahead and do the calculation. It's nothing but it's a simple dot operation. Okay. So here I will just go ahead and write. If you just do the multiplication operation, final output that I'm actually going to get is 1, 0, 0. Okay. Then I have 1, 1, 0. And then I have 0, 0, 0. Okay. So this is my final matrix. And that is what we have done. We have done the multiplication of 2 important metrics, mask metrics in short. Okay. And this is how you have actually got it, right? Then the next step in this will be that wherever the value is 0, please listen to this very, very carefully. Wherever in the combined mask, the value is basically 0, there we specify, okay? There we specifically specify infinity, okay? The reason I will tell you, okay? Why do we specify infinity? But let us do one thing. Let us do all the steps for this particular data that we have created, right? For this data. So here, I'm just going to copy this particular data because we are working on this. And here we discussed about masked application. We saw example and finally we got the combined mask. Now for this data, we will go ahead and compute our mask. Okay. So let's go ahead and compute our mask. So here you could see this was my score, right? And with respect to this particular score, now let's go ahead and find out our look ahead mask. So here I'm going to go ahead and compute my look ahead mask. Now, in order to get the look ahead mask, it is very simple. Here, how much I have? 4 cross 4, right? Now with respect to 4 cross 4, again, this will be 1, 0, 0, 0. Then the next one will be 1, 1, 0, 0. Then I have this 1, 1, 1, 0. And then I have finally 1, 1, 1, 1, since it is a 4 dimension, right? And here, this is my complete look ahead mask, right? And similarly, if I want to get the padding mask, okay. So in order to get the padding mask, and with respect to the padding mask, I know I need to have this in the extended to 2D format, okay. Single format, it is very simple, but 2D format, what we really need to do over here is that I will go ahead and write 1, 1, 1, 0, because this is not important. Then again, I have, this is dependent on this, this is dependent on this, this is in turn dependent on this, dependent on this. So I'll again go ahead and write this one. Then I will be having my third one, 1, 1, 0. And then the fourth one will be nothing but 0, 0, 0, 0. Okay. So this is my padding mask, right? Now, when I want to probably create my combined mask, so it is nothing but, if I want to probably find out my combined mask, it is the product of look ahead mask multiplied by multiplication by padding mask. Now, how are we going to do this particular product? It is very simple. It's more like element wise multiplication. This will get multiplied to this, this will get multiplied to this, like that, right? So finally, if you go ahead and do this calculation, it is nothing but 1 multiplied by 1, 0 multiplied by 1, 0 multiplied by 1, 0 multiplied by 0. Okay. The next one will be nothing but 1 multiplied by 1, 1 multiplied by 1, 0 multiplied by 1, and 0 multiplied by 0. Okay. Then again 1 multiplied by 1, 1 multiplied by 1, 1 multiplied by 1, 0 multiplied by 0. So when we say multiplication, this is nothing but dot wise multiplication. Okay. Element wise multiplication, sorry. 1 multiplied by 1, 1 multiplied by 1, 1 multiplied by 1, and here I have 1 multiplied by 0. Okay. So finally, this is my output, and the output is very simple over here. I will be getting 1, 0, 0, 0. Then I have 1, 1, 0, 0. Then I have 1, 1, 1, 0. Then I have 1, 1, 1, 1, 0. So this is my final combined padding. This 0 is there basically to ignore all the tokens, padded tokens, and wherever there is 1, those are very important. Okay. Now the next step, which is really, really important, okay, which is about masked scores. We go ahead and compute our masked scores, and it is very simple. The masked score is nothing but wherever there are zeros, that is going to we'll just go ahead and add. You can just basically do something over here. Okay. So let's see this. Okay. Now here I have my combined mask. Okay. Now for getting this combined mask, for applying this combined mask, what we'll do, we'll apply this combined mask to this entire matrix. Okay. And the next step that you'll be seeing after this will be that we will try to convert this into a mask over here. And in this, instead of 0, here we are going to convert this into minus infinity. Why minus infinity? I'll just talk about it in a while. Okay. So here my next step will be converting everything into minus infinity. The reason is very simple, very, very simple. Just think over it. Till then I will go ahead and write this minus infinity. Wherever there is 0, that will get converted into minus infinity. Okay. So this in turn, I'm actually getting in the form of minus infinity. And again, we do the dot wise operation with this, right? Wherever there is minus infinity, that will become minus infinity. Okay. So final mask score, you'll be able to see that. I will go ahead and just do the dot operation. So I'm going to get 0.3 minus infinity, minus infinity, minus infinity. Okay. And then you have this 0.7, 1.9, minus infinity, minus infinity. Then similarly, you have 1.1, 3.1, 5.1, and again you have minus infinity. Then you have 0.0, 0.0, 0.0, then again you have minus infinity. So this is your final mask score. Now, the most important thing that you really need to understand is why you need to have this minus infinity. So here you'll be able to see that one minor mistake that I did was that I told, hey, we are replacing 0 with minus infinity. No, minus infinity is getting added to this specific 0 value. Okay. And why this is actually done is that I will just go ahead and write the reason over here. Okay. When we apply or when we try to, add this specific value, okay, it is basically to zero out, or it is to remove the influence, zero out the influence when the softmax activation function is applied, because the next step is applying softmax activation function. Okay. Now, when we apply softmax to minus infinity, you'll be seeing the answer, what you'll be able to get. Okay. This is crucial. This step is crucial to ensure that certain position, right? Example, if I probably consider padded tokens or future tokens in the case of look ahead masking do not affect the attention mechanism. Okay. And obviously the impact of zeros will also get removed, right? When we apply a mask, we need to ensure that a certain tokens do not influence the attention mechanism. We achieve this by setting the attention score for these tokens to a very high, large negative numbers. When the softmax function is applied to the scores, it converts this entire value will be getting converted to 0. Okay, ensuring that there is no much influence on the attention weights. So attention weights will not get impacted, right? Because after this, after we calculate the mask scores, what we are specifically going to do, okay, we have to probably convert or apply a softmax activation function. I hope everybody knows that, right? So that is what we are specifically going to do over here. Over here, we are just going to go ahead and apply our softmax. That is our next step. So let's go ahead and do the softmax, because after this, we'll go ahead and add our values, right? So softmax scores that we are going to get is nothing but softmax. And here I'm going to use my masked scores, right? Now with respect to the mask scores, when I apply the softmax, here you'll be able to see that I will get 1.0. I've done the calculation. Minus infinity is basically going to convert into 0. Okay. You can go ahead and write this, or you can also check it out. This will be 0.3, 0.7, 0.0, 0.0. Okay. Then I have 0.3, 0.6, 0.6, 0.0. And then I have 1.0, 0.0, 0.0, 0.0. So this is my entire score that I'm actually getting. Okay. And then, as you know, in the self attention, the final step will be that we will do the weighted sum of values, right? So every number over here inside this softmax is going to get multiplied by this softmax score. Okay. Is going to get multiplied by V. Okay. So here my attention output will be nothing but it will be softmax scores multiplied by the vector V. Okay. So guys, this is the step-by-step mechanism that specifically happens in the decoder, which is similar to encoder, but one additional step that you were able to find out was about masking, right? And what is the importance of masking? I will be giving you in this specific PDF in the word of writings so that you'll be able to understand. Masking in the transformer architecture is essential for several reasons. It helps manage the structure of sequence being processed and ensures the model behaves correctly during training and inferences. Here are the key reasons for using masking. One is basically to handle variable length sequence with padding masking, because there will be many number of zeros. To handle sequences of different length in a batch to ensure the padding tokens which are added to make sequences of uniform length do not affect the model prediction. And second is basically to maintaining auto-regressive property with look-ahead mask, right? The purpose is very simple: to ensure that each position in a decoder output sequence can only attend to the previous position or itself, but not future position. This is crucial for sequence generation tasks like language modeling and translation, where the model should not have the access to the future tokens while predicting the current token. Okay. So these are some of the important steps with respect to the masking. And now the next step that we are basically going to discuss about is add and normalization. And then what is this exact line and why this particular line is also coming up. Okay. So that is what we are going to discuss about in the next video. So yes, this was it from my side. I'll see you all in the next video. Thank you. Hello guys, so we are going to continue the discussion with respect to our decoders. Already in our previous video, we have discussed about this really important topic which is called as masked multi-head attention. And we understood how different types of masking is specifically done and what is the purpose of the masking, right? Then after this, adding a normalization will specifically happen over here. And when I say normalization, layer normalization will basically happen. And this is the same layer normalization like how we discussed in the encoder, right? So from here, you'll be able to see a residual connection is basically there, which is also called as skip connection. So this skip connection information is also going, right? So I will also go ahead and say skip connection, okay? And with the help of this, what will happen is that it will get added to the output vectors that is probably coming from here, right? And how did we calculate the output vector? Step by step, each and everything is probably shown in the previous video, right? We went till the Softmax and we probably found out the Softmax scores. And these were the scores with respect to the vector that I had, right? Now, what we are going to discuss about in this particular video is about encoder and decoder multi-head attention. Okay, so this multi-head attention is also called as encoder and decoder. Why it is specifically called as encoder and decoder, we'll just discuss about it. And you'll be able to see that two of the connection is specifically coming from the encoder output, right? So here from the encoder output, when I say encoder output, from here we are specifically taking the vectors of key and values, okay? So we are going to probably take the vectors of key and value that is coming outside this particular encoder, and we are going to give it to the decoder multi-head attention. So from here, you'll be able to see from the adding and normalization layer, what information will be going from here, whatever query vector is basically generated, right? That will specifically be going. Now you may be thinking, why query from here and why key and values from the encoder output, okay? The reason is very, very simple. So here you'll be able to see from the encoder, right? From the encoder output, right? What we are specifically sending, we are sending a set of attention vectors, attention vector K and V, right? And other than this, you'll be able to see when the output from this, right, masked multi-head attention. So the output from masked multi-head attention, here we are sending attention vector Q, which is also called as query vector. Now this query vector is the information that we are specifically doing over here, right? By shifting the outputs to the right, then we are getting the output embedding, then we are probably getting the positional encoding. Okay. And there is one very important thing also I really want to discuss based on your input and output, and just I'll discuss it in another 5 minutes. Okay. And why we are specifically doing it is very much simple, because you can understand that these keys and values, these are to be used by each decoder in its encoder decoder attention layer. And why specifically we are doing this? Because this helps, this entirely helps the decoder to focus on appropriate places in the input sequence. See, during the training time, I know here we will be giving out training output, right? Whatever will be my y, and we need to predict y hat, right? So over here, with respect to what will be the query of y, with respect to this key and values that is coming from the encoder output, that both will be given, means a set of 3 vectors of k, v and query, which is coming from this masked multi-head attention. It will be given to the multi-head attention, which is also called as encoder decoder multi-head attention. And based on this, whatever is the necessary operation that specifically takes in multi-head attention, right? So in the multi-head attention, what will happen? Self-attention will specifically happen inside that. Then you go ahead and multiply the query with keys. Then you apply a Softmax. Then you multiply with the values. Then you probably calculate the scores. That exactly we have discussed about each and everything when we had discussed in the previous session, right? Where we have discussed about all the numericals, what is going to happen, right? Same thing is over here. That is specifically going to happen. The K and V are going to come from the encoder output, and query is basically going to go from here, right? Then all the necessary operation will take place while the training, and then after this again adding and normalization will basically happen. And again here also you will be able to see whatever output I am getting over here, right, with respect to the queries, that will be also forwarded to the next layer, that is called as adding and normalization. This is just to make sure that more added information is gone to the next layer, right? So by this, you will be able to understand that what multi-head attention will specifically do. And the major thing that is important for you all to understand that for this multi-head attention, from where the encoder output is probably coming up, what is the encoder output? That is the set of key value vectors, and the query vectors will probably come from here, right? And why do we do this? See, at the end of the day, when you have a data set, right? So when you have a data set, in this data set, you have some input and output, right? In input, let's say you have x1, x2, x3. In the output, you have y1, y2, y3, right? So while training, I have to pass x1, x2, x3 over here, right? So when we have these inputs, we need to pass the inputs from here. All the process will basically happen. And with respect to that, while we are training this entire transformers with respect to our input and output, let's say the example that I'm actually going to take is about machine translation. So here also we need to pass the output, which will be my y, right? Y. Again, output encoding will happen, positional encoding will happen. Then after that, masked multi-head attention will happen, right? We have discussed about what masked multi-head attention is all about, right? But when we come over here, we need to make sure that based on this particular vectors, we need to map the key and value vectors for this. So the training mechanism will definitely know that how this query can be matched with this K and V, so that we will be able to, focus on the appropriate places in the input sequence to probably predict the next word, right? And this is really, really much important for you all to understand. Okay. Then after that, you have this feed forward neural network and adding a normalization. This is the same thing that what we discussed in the encoder output. Now let me do one thing. Let me go ahead and show you one of the most amazing diagram. And by this, you'll get a clear idea how the entire training basically happens. So again, this is the blog from Jalamar and beautifully transformers has been explained over here. What I have actually done is that I've put up more stress on the research paper to explain you each and everything that is going behind the hood. Okay. So see over here. So decoder side, what it happens is that we know the components of decoder work as well. Okay. The encoder starts by processing the input sequence. So from here, all the input sequence will basically start. The output of the top encoder is transformed into a set of attention vectors K and V. So from here, I will be getting this K encoder and V encoder, right? Then they are used by each decoder in its encoder and decoder attention layer. Okay. So that is where we are specifically using them inside our decoder, where in the encoder and decoder attention layer, which is nothing but encoder and decoder multi-head attention, which helps the decoder focus on the appropriate places in the input sequence. Okay. Now let's see this. Okay. At timestamp 1, okay, we need to pass this entire information. See, at timestamp 1, this is the word JE. It goes to the encoder. I mean, all these three words, JE, Suis, and Intudent. Then this vector is basically created. Then from this, we derive our K and value encoders, right? And this is passed to our decoder. For every decoder, we specifically need to pass. And initially, we don't pass anything for our training data set. Understand one thing, okay? So this is really important to understand. See guys, initially, we don't pass any training data set, okay? From the second instance, once we generate this, then we will be passing our training data set, okay? While the training phase, I've also seen in some of the research paper where they say that, hey, the first word needs to be passed and based on that, some prediction needs to be done. But again, in some research paper that I was seeing and in some of the blogs that I was seeing, here a start token will specifically go. Okay. So let me do one thing. Let me open my Epic Pen so that I will be able to explain you here also. Okay. And you'll be getting a clear idea like how things basically happen. But this diagram will actually showcase each and everything. So here I have got my encoder. Okay. Now the next step, this is my K and V value encoders. So here what will happen, the first state start token will go. Okay. Now this start token, when it goes, again, this will be done with respect to embedding, positional embedding, everything. It will go to the next step. Then in our multi-head attention, right, this KV value will be taken, and whatever query vector is basically generated from here, that will be given to the multi-head attention along with this, right? And similarly, the next step will go. Once I is computed, what will happen? For timestamp 2, when we are doing the decoding timestamp of 2, something is going to happen in this way. See this. So for timestamp 2, see, let's start this entirely from starting. Okay, so from timestamp 2, what will happen? I will come. The previous output is I. Then it is going to go, right? Then all the steps inside the decoder will basically happen. This will be your encoding and key and value vectors. But with respect to every word that you are specifically getting over here, positional embedding will happen. And with respect to this particular word, your query vector will be created. Okay. Don't worry about linear and softmax. I'll discuss more about this in the next video, but I hope you are able to understand this, right? In the first instance, I will just pass a start token. It will take this, it will generate a query vector for that. It will take this, it will pass it to our multi-head attention. You know what are the steps in multi-head attention, right? But at timestamp is equal to 2, whatever output is basically generated over here, like I, that will get passed over here. Like previous output will be this, right? And then again, for this, vector is basically created. Again, key and value vector will be created. Then we go to the next step where our next word will get predicted. Similarly, we'll go and take this previous word, give it to the input into the decoder. Then again, the third word will go and give it to the decoder, and finally we'll get the output over here. So this sentence that is probably given over here, it will getting converted in this specific way, right? So I hope you got an idea of this, right? So let me just go ahead and explain it once again. Okay. So here, let's say this is my encoder, right? You know what is there in the encoder, right? So in the encoder, I pass all my words after doing the positional embedding. Let's say this is my output. From this, we take all our key and value vectors. We give it to our decoder. In the decoder, for the first phase in the training, we give a start token. Okay. Then what will happen? It will go to that masked multi-head attention. Then it will go to the multi-head attention, which is also called as encoder decoder. For this, K and V will be going from here and query will be going from here, right? Then we go to the next step. So I've just drawn a rough diagram, but I hope you are able to understand it over here, right? So I will just close this again and let's do one thing. Let's quickly take this image. Okay. So I will copy this image and I will paste it over here. Okay. So please make sure that you have this entire steps recorded. Okay. So what we do in the first decoding timestamp, we give all the words, we generate all these things, right? We don't give anything from here. Instead, what we'll do some kind of padding. We'll create a start token, right? Initially, and then we'll go and generate this output I, right? Then I will be sent with respect to the previous input. Then we'll go ahead and compute the M. So this will be M. Again, M will be sent in my third timestamp, right? Similarly, all the further timestamp things will basically be happening. Okay. So over here, you can see at timestamp 2, whatever output is basically generated at timestamp 1, I, that is sent as the previous output. Okay. So I hope you got an idea with respect to the multi-head attention, and you know what happens inside multi-head attention. I don't need to explain that because already we have discussed in this. This is the entire training mechanism. Try to understand in this specific way. Training mechanism. Okay. In the training mechanism, initially what is going to go over here? Then once we generate this particular output, this same output will be going as an input to the decoder for the next timestamp, right? So like that, we go ahead and continue it. So I hope you got an idea with respect to encoder and decoder multi-head attention. Now it's time that we understand the most important thing, that how do we calculate our output probabilities? And that is what we are going to discuss in our next video. So I hope you like this particular video. I will see you all in the next video. Thank you. Hello guys. So finally we are into the last stage of understanding about transformers. I know this entire series now probably is more than 5 hours of content, but you can just understand why this entire architecture is so amazing, right? It looks complex, but if you break down this entire architecture, you will be able to understand each and everything. And that is what, while explaining all these topics, I have actually done, right? So from starting from positional encoding to multi-head attention to feed-forward neural network, here also we discussed about masked multi-head attention. We went to multi-head attention. We also covered about feed-forward neural network. Now it's time to understand about the final layer of the decoder, right? That is nothing but linear and softmax layer. And through this, we basically go ahead and calculate the output probabilities. Now I will try to just make you understand. Again, this entire diagram is from that amazing blog, right, about transformers. And what I will do is that I will also go ahead and share that link with you all. Okay, you can go ahead and refer it. So till here, what we have actually seen, we have seen all the kind of operation related to Q, K, V. Here, Q and K is basically going, V is basically coming from here. And again, we also have a lot of multi-skip connections, like from here to here, we are passing some information regarding positional encoding, then other information I'm passing it over here. Now let's finally do one thing. See guys, after this decoder is completed, right, at the end of the day, you are just going to get vectors, right? Now, how do we convert this vector into a word? That is what we are going to see in this session, right? So our main aim of this particular session is that how we will be able to convert our vectors into our output word. And that is what I'm going to discuss step by step. Now, first of all, here you'll be able to see there is something called a linear and softmax. First of all, we'll try to understand what exactly is this linear. So to begin with, this linear, or I will just go ahead and write the linear layer is a simple, fully connected neural network that projects the vector produced by the stack of decoders. Okay, stack of decoders. And it basically generates a very large vectors, which we also called as logit vectors. Okay, logits vectors. Now I'll talk about what is the importance of this logit vectors, and this is what a linear layer basically does. Okay, linear layer basically does. So let me go ahead and explain. A linear layer is a simple, fully connected neural network that projects the vector produced by the stack of decoders, right? And it basically generates this into a large vector, which is called as logit vectors. Now, what exactly is this logit vectors? Okay, so we'll try to understand this. Let's say if our model, we have a specific model, if let's say our model knows more than 10,000 words, right? Let's say that there are 10,000 unique words and this is my entire vocabulary, right? So in this case, my logit vectors will be 10,000. Logit vectors will be 10,000 cells wide. So here, instead of just having this many vocab size, we'll be having this 10,000 vocab size, okay, or logit size. Now, understand each and every block that you see in this logit vectors, it corresponds to a score of a unique word. So here, this specifically corresponds to a score of a unique word. What kind of score? We will talk about it, right? It's just like mapping a vector to words, right? So for this, once I probably get all the vectors from the stack of decoder, I'm going to pass through the linear layer. It is a fully connected neural network layer. And once we pass through this is going to give us an output of this much nodes, right? This many number of outputs of a vocab size. So number of words vocab, right? So again, over here, you'll be able to see, it will take this particular vector and it will convert this into logit vectors. Okay. Then if you go to the next step, it is a softmax layer. Now, you know why softmax layer is used. It is specifically used for multi-class classification. Multi-class classification. Now, in the case of multi-class classification, what will happen? As soon as I pass this particular vectors, every vector is basically going to give us our log probabilities, right? Now, this probabilities means what? Let's say if this vector has the highest probability, right? Or if this word has the highest probability, then my output will be this specific word. If this word has the highest probability, then the output will be this specific word. Okay. So here in the second step, what we are basically doing is that the Softmax layer turns those scores into probabilities. Now, since it is turning this into probabilities, if I probably do the summation, it will all add up to 1, right? That I hope everybody knows about, because that is the property of Softmax layer. Then the cell with the highest probability is chosen as the output, is chosen, right? And the word associated with it is produced as the output, right? For that specific timestamp, okay? Or for that specific timestamp. Now, I hope you are able to understand it, okay? So whatever output I get from the decoder, that is passed to a linear layer, which is a fully connected layer. And this output will be based on a vocab size, that many number of cells. And once this is passed to the Softmax, I will be getting a probability, and whichever has the highest probability, that will be my output word, okay? When we say vocab size, see, vocab size basically means if there are 10,000 words, for every index, there will be one word, okay? So more to talk about, let's go through the entire training process now. So here I will talk about the recap of training. And here also I will take multiple examples. Let's say in my entire vocab size, I have this many number of vocabs. Let's say this many number of words are there. So in my vocabulary, I have A, am, I, thanks, student, EOS. Okay. So that is the reason I've given this as indexing. Okay. Now for the first instance, what we do, if I don't just use a simple embedding technique, okay, I will just go ahead and use this simple embedding technique. So for every word, what we will do is that we will try to use one hot encoding to represent it. So let's say this is my one hot encoding. Okay, this is my one hot encoding for the word M. Okay, so wherever M is present, since the vocabulary size is 6, so I will write 0.0. Where M is present, it will become 1.0, 0.0, 0.0, and 0.0. Okay, now, so during the loss function, what will happen? If I have started training the word, okay, if I have started training the word, and similarly, like if I want to have thanks, then this will become 1 and remaining all will become 0. Let's say that I have a problem statement where I need to convert this mercy, right? Mercy, I think it is in French. We need to convert this into thanks, right? And vocabulary size is over here for me, okay? So what will happen if I have an untrained model, right? My initial output may be something like this. See, I need to get this word, right? Thanks. So I need to get this value as 1.0. But if we see with respect to the untrained model, initially you'll be able to see these are different values. I may get different values for each and everything. Okay. So this is how my output should come, but this is how I'm getting the output, right? So after this, what we do, we basically go ahead and calculate the loss function. Okay. Loss function. Now this loss function is really important. That is where your back propagation will specifically happen. Okay. And just to make you understand, let's say I want to completely frame this particular sentence. Okay. So just, I'll take an example. Okay. I have a task where I give this words and it should probably form a sentence for me. Okay. So here I have A, M, I, thanks, student. If I really want to know the output, it should be like I am a student and thanks we can basically write, right? I can basically say thanks. Okay. Or let's say I don't want to use thanks or even, because thanks will not be a very good thing in that particular sentence. Let's say if I give this particular word, I need to frame a better sentence. So here I can frame one kind of sentence like this. I am a student. And then we should basically get our EOS, right? So in this particular scenario, what will happen is that for positions also, right? For position 1, what will be my target model output and all. So for the real output, my target output in my output feature will be something like this, right? So my input is something like this. Let's see. I will just show you over here. Okay. Let's say my input over here in my data set, and this is my output. In my input, I have words like AMI, thanks. Okay. Not thanks, student. Let's say I will go ahead and write student. Okay. Now my output is, I will go ahead and write, I am a student. Okay. Let's say this kind of output I really need to get. Now here, based on this particular actual output, I should be getting, like if I consider my vocabulary size as 6, I should be getting something like this, right? My position 1 should be I, position 2 should be M, position 3 should be position 4 should be student, and then finally end of statement. But what happens is that while we are training, with this particular data set after some epochs, during initial training, you will be seeing that, hey, my output will not be that good. But after training for some time, let me just go and show you. After training for some time, you'll be able to see over here, I will be able to get something like this. I will become 0.93, then this will become 0.8, 0.9, 0.94, 0.98, right? And this is all because of loss function and epochs. And this all keeps on getting updated, okay? And that is what I really wanted to show you as an example. But at the end of the day, you'll be able to see that we will initially be doing encoding for this. Here we have just used one hot encoding. Different encoding can also be used, right? Untrained model may give you some kind of output, but again, we need to go ahead and compute the loss, and then we will do the back propagation, and then we will go ahead and compute all the weights, right? With respect to all your training data and all, right? So back propagation, the main aim is to reduce the loss, right? So after training from some specific outputs, initially my training model output will be like this, right? If I convert each and every word into one hot encoding, one hot encoding, one hot encoding, one hot encoding, right? One hot encoding. And this is with respect to position also. In position 1, I is basically having 1.0. So this is what is the one hot encoding for this. Then you have this, then you have this, then you have this, right? So once you do this, this is what is my output that I need to get. But my model, when it initially generates, it can generate something else, right? Then a loss will be calculated between both of them, and it will be reduced till we get this kind of values. And once I get this particular model out, and this is after the, you can probably say with respect to your fully connected layer, right? Over here. So the linear layer, that is what I'm actually talking about, right? And then once you probably compute the loss, you will again be doing back propagation. So this was overall the final linear and softmax layer, but I hope I tried my level best, whatever was possible. But just imagine guys, 34 pages I've actually written just to explain this research paper, broken down each and everything, tried my level best, okay? But yes, there may be again some things that you really need to revise from the research paper, but I tried my level best, whatever was possible from my side, okay? But I hope you're quite happy with this explanation, and I hope you're able to understand each and everything. So yes, this was it from my side. I will see you all in the next video. Thank you.